And when you join them, all you do is need to make one connection a year, and that will be an investment in your career, in how to be a professional, how to see where the community is going, what are the new trends, how you should behave yourself, how you should think as a professional computer scientist, computer engineer, software engineer, or other information professional. These are the benefits. These are the real benefits. You are investing in yourself when you join, because it's through these connections that you really learn to be a professional. Information, you can get that on the internet. Professionalism, you get that from the IEEE Computer Society. We have a web page below that you can click on to renew your membership. Thanks for listening. Take care.
Computing is expansive.
Computing is evolving.
Computing is limitless.
We are the IEEE Computer Society, the professional home for all computing.
We bring together passionate engineers, scientists, academics, and industry to cultivate environments for idea exchange, dialogue, debate, and collaboration.
We set the standard for learning that empowers, with peer-reviewed publications and international conferences, local chapters and meetings, and valued resources.
We support members, we cultivate leaders.
We help computing professionals at every stage of their career.
We are the IEEE Computer Society, your professional home.
Good morning, good afternoon, good evening, and good night.
Hello, everyone. Can you hear me?
Yes, we can hear you. Thank you.
Thank you. Thank you
Yeah.
for today with us. It's our pleasure to start our next Computer Society Distinguished Visitor Program EXA event for 2024. I'd like to welcome all of you. I will just share with you a few words from Giorgio Perler, the IEEE Computer Society Distinguished Visitor Program. Unfortunately, due to travel arrangement, he will not be able to present online, but he shared with us some more. So let me just share it with you.
Good morning, good afternoon, good evening, and good night. A greeting adapted from the movie The Truman Show, starring Jim Carrey. And it works here, since to each of you, there is some relevance in that greeting. And hello, Kuala Lumpur, Sapporo, San Francisco, Wilkes-Barre, Thule, Dublin, Bruges, Cairo, and Mumbai. I'm George Proler, Chair of the Computer Society Distinguished Visitor Program, and it is my honor and privilege to welcome you to this, our second annual IEEE CS EXA DVP event, or as we call it, the 24-hour event. second annual, has a nice sound to it. At the beginning of last year, hosting such an event was just a thought. To extend an earlier project to cover an entire day, 24 hours of presentations, reaching and including our diverse membership. And quite frankly, we were unsure if we could put it together. But Professor Hassam Fahmy, my predecessor, and Professor Islam Halim, chair of the Awareness and Customer Advocacy Committee, and his team rose to the challenge. And we did it. And it was successful, the first annual. And now, well, Professor Islam and his team have outdone themselves. Look at the agenda for the next 24 hours. Artificial intelligence, AI security and privacy, and research ethics in the area of AI. Quantum computing and the quantum world, smart and high performance computing, and the list goes on. And we are already working on the planning for the third annual event for next year, taking another step and upping the challenge for Professor Islam and his team, as we are looking to make this a hybrid event with on-ground activities concurrent and shared with the online participants and attendees. This event spans each of IEEE's 10 regions and the world's time zones, hence my adapted greeting, since each of you and the DVs, the presenters, the moderators, you all hail from different and diverse regions. And for some of you, it's 10 a.m., 2 p.m., 8 p.m., and 2 a.m., and all the hours in between. So it is morning, afternoon, evening, and night. Truly an effort of inclusion of our diverse membership base. Today is International Volunteers Day, which is fitting, since it has taken, and before this day is through, it will take the efforts of more than 50 Computer Society volunteers coming together from the Geographic Activities Committee, Students and Young Professional Activities Committee, and the Distinguished Visitor Program to bring this event to you. Over the next 24 hours, you will have the opportunity to attend more than 20 technical presentations on topics I've already mentioned, along with informational talks about the Computer Society and its regions, activities, and programs. Each presentation will be introduced by an event moderator who are members of various student chapters, and through participation in this event are gaining experience and opportunity. And then there is the audience. That's you. Many of you are members and affiliates of the Computer Society who volunteer your efforts to make local programs a reality. And all are here allowing us to bring this event to you. So thank you for your time. And now, before I wear out my welcome, I'd like to pass the baton to Professor Irinori Washizaki, the President-elect of the Computer Society. Thank you.
Thank you. Thank you so much. So, Professor Hirono, are you, we'd like to welcome you and
Sure.
give you the floor to share your thoughts and ideas.
All right. You see me? Okay.
Yes.
All right. So good morning, or good afternoon, or good evening. Hello, everyone. All organizers, supporters, distinguished visitors, art professionals, and students. Thank you for inviting me to this precious occasion. I'm Hirono Washizaki, IEEE Computer Society 2025 President. So on behalf of the IEEE Computer Society, it's my great honor to welcome you to this second IEEE Computer Society EXA DVP event 2024. I'm so delighted to see that since its establishment, Distinguished Visitors Program has provided a great opportunity to bring the excellence, expertise of world-class technology leaders and also innovators to chapter events. So congratulations on having this very inspiring event. As we gather here today, we are reminded of the critical role of computer science and engineering in our digital and AI-empowered world. So this event allows us to bring together leading researchers, scientists, engineers, and industry experts to share their insights into smart computing, AI, and also related areas. So talking about AI, I have read the evolution project of the IEEE Society Guide to the Software Engineering Body of Knowledge, or in short, SWBOK Guide. So the latest version 4 of SWBOK Guide was just released. So that incorporates the connection between software engineering and AI. So like this, Computer Society has led the way in new technical areas, such as AI, and engaged students, early career professionals, industry individuals, and organizations. So I often refer to an African proverb. It says, if you want to go fast, go alone. But if you want to go far, go together. So let's grow this community and go together to go beyond current AI and smart computing, and also limitation of current diversity and inclusion and world's sustainability. IEEE Society is always your professional home, and your visible feedback and action will shape the society to change the world and contribute to humanity. So finally, I extend my deepest gratitude to the organizers, supporters, volunteers, speakers, and all of you attendees. Your dedication to excellence in computing is so inspiring. Thank you, and I wish you all a productive and inspiring event. Thank you.
Thank you, Professor Hironorio. It's our pleasure and honor to be here, and I'd like to thank you for, even though your limited time. Thank you so much.
Yes, thank you.
I'd like to move to Dornita, the past president for the Computer Society. It's our pleasure to have you today.
Yes, thank you, Dr. Halim. Very good evening, good afternoon, good morning to everybody on the call. It is very exciting to join you today as you prepare for the second annual. You know, usually the first people say is very difficult, but I kind of disagree. I think the second can be more difficult because you have to sustain energy, excitement that was started, and then you also have to continue paving the road. And so it's incredible to see everyone gathered today to continue this path of having our distinguished speakers come together and to truly have an event across all parts of the nation and the countries and the technologies. I'm excited to see the wonderful lineup. And as George mentioned in his intro, it is Volunteers Day, and we couldn't do this without the incredible work of volunteers from students, professors, industry all across the globe. One of the things I want to share with you is that when you are putting in this work and you think no one notices, that is probably the biggest impact that you have, because when you think no one notices, that's where most impact happens, because people are so overwhelmed with the work and they take it a little bit for granted. So it may sound counterintuitive, but when somebody takes something for granted, that's when they most appreciate the work, and they won't recognize you, but you personally should take that joy of, hey, somebody thought this was so easy that they took it for granted, because that's where you make the impact. So I want to thank you for your work. I will say that I recognize all the hours, all the information, all the connections you have to do to make this happen, and I thank you for that. Enjoy today.
Thank you so much for your support, and it's our pleasure and honor to have you. Now I'll leave the floor for David, the MJA Vice Chair and Chair of Geographic Activities Committee. And actually, this work wouldn't be done without your continued support for us. Thank you for all kind of support you provided, and it's our pleasure to welcome you and know your thoughts about this event. Please, Dave.
Yeah, thanks, Islam. Welcome to the Computer Society DVP EXA event from the Geographical Activity Committee. Islam, our Region A coordinator, has been working with the DVP committee to create this unique event for the second year. I hope you enjoy these quality presentations that fit into your time zone. I will be back at 2030 GMT to talk about Beyond More, 3D memory and 3D packaging. So I hope you'll attend. And thanks, Islam, for putting this all together.
Thank you. Thank you. Now, I think we have to move to hear from Professor Hussam Fahmy. He shared with me the slides. I'll try to just run it.
I am Professor Hussam Fahmy, Professor of Computer Engineering, Faculty of Engineering and Shams University, Cairo, Egypt. I am the immediate past chair of the IEEE Distinguished Visitors Program. Good morning, or good afternoon, or good evening. It is 3 a.m. Cairo time. Welcome to this year's IEEE Global event. It is both an honor and a privilege to participate in the opening ceremony as we embark on this remarkable journey of innovation and collaboration. We gather not just to celebrate the advancement in technology, but to recognize the collective spirit of curiosity, ingenuity, and perseverance that unite us as a global community. IEEE has always been at the forefront of shaping the technology landscape, and this event exemplifies our shared commitment to advancing technology for humanity. Over the next 24 hours, we will witness remarkable talks and engage in thought-provoking discussions. This year's theme, International Volunteers Day, serves as a powerful reminder of our responsibility as innovators and leaders. Whether we are addressing pressing challenges such as sustainability, connectivity, or ethical AI, we stand united in our mission to create a future that benefits all. I want to take a moment to express my gratitude to the organizers, volunteers, and sponsors who have worked tirelessly to make this event possible. Your dedication and passion are the foundation upon which this event stands. Our participants, researchers, industry leaders, and students, you are the heartbeat of this gathering. Your ideas and contributions make this event truly global and impactful. Islam Sarwat, go ahead as usual. George Froller, David Bandurant are usually at the core of success. Hironori Washizaki, all the best in your coming moves. As we open this global event, let us embrace the opportunity to learn, innovate, and inspire one another. Let the exchange of knowledge and ideas begin just after this opening. Thank you, and may this global event be a resounding success.
Thank you, Professor Hussam, and thank you for all our guest speakers today for the opening session. But by the way, Professor Hussam was my professor during my master and PhD degree, and he nominated me to Giorgio Proler maybe 4 years ago to join to volunteer with the IEEE Computer Society. And I'm grateful for his support, continuous support. And I truly believe that the IEEE Computer Society has changed my career and supported me along this. My message to all our young and students and the young professional, the IEEE Computer Society is our second home, and by volunteering with it, it's really have great impact for our career and our professionalism. So thank you all for your continuous support. Now I just maybe go quickly to share with you our program for today, if you allow me. We'll start maybe in 10 minutes. We'll start with region 10 sessions. Start with Dr. Muhammad Rawdan to give us insights and thoughts about region 10 activities. It's really important to share with us and the community those kind of activities. I'll be honored to moderate his session. I just need to share my screen. So after that, we have 3 DVB talks. It's really important to know more technological talks about some security, some quantum computing, and distributed systems. It's also as our main theme for the DVP EXA events is to include and to show our commitment for the inclusion and our support. So it's really important to include student young professional with us. So we have talks for the SYB. Shavim, the past chair of the SYB, will lead this session, and the moderators as well from the SYB team, in order to allow them to have more interaction and get more experience with their leadership. After that, we have 2 talks from the DVB as well. It's really about the security. The session should be moderated by the area coordinators or chapter chairs. This for the upcoming maybe 7 hours, and will be hosted at Region 10. And I'd like to take the opportunity to thank Professor Muhammad Rawdan, the Region 10 coordinator, for his continued support. It's really our pleasure to work with him. For the second part of the event, we'll move to Region 8, my region. However, I'll do my role as the DVP ACA chair. So I thought we need the support from our area coordinators. So I left the session of Region 8 for my colleague Katrina from Macedonia. I think I have to also share it again. This the next part. So we'll start with Region 8 talk. It will be provided by Katrina, my colleague in Region 8 committee. After that, we have also 3 DVP talks from distinguished visitors from Region 8, from Costas, from Isabel, from Professor Anne. It's related about research ethics in AI, the smart toys, and the high performance computing. After that, we'll provide 2 talks for the SYB and DVP. Then we'll finish as well with DVP talks from Professor Francesco and Professor Adel. Those sessions also are moderated by some of our area coordinators. I'd like also to thank Professor Ahmed Hassan, Area 6 coordinator, and Zorika, Risala from Bahrain, Dr. Maggie from Egypt, and the student and the SYB DVB will be moderated by our young volunteers, Imtiaz and Shataksh. After that, we have also 30-minute break. Then we move to Region 9 to start with talk from Roberto, the Region 9 coordinator, and a talk from our DVB Pablo about some interesting talks. Then the third part will continue, of course, in Region 9 with other but we'll try to focus to have more engagement with the SYB team. So we have several talks from Karim, Christiana, Anand, Eric, Juan, and maybe we need more DVs in Region 9 in the next year. Then we will move to Region 1 to 7. It's our pleasure to be hosted maybe from my colleague Region 7, Faris. So he'll give us some talks about the region. Then we will move to have the talk from the JAC chair, David. After that, we have 2 DVB talks about the machine learning and robots. Then we'll finish with the SYB and DVB talks for Region 1 to 7. And finally, we'll give our last DVB talk from Mike Chan. So hopefully 24 hours of very fruitful talks and discussions. And I hope you can enjoy and get more benefit from the day. Thank you for your support. Thank you for being here. So just have a few minutes break, then we'll start our session. Thank you.
So, Dr. Halim, I have a quick question. Like all the sessions, we have the same Zoom link, right?
Yes, Dr. Yes, the same Zoom.
Okay. Okay. Thank you
It's
so much.
continuous 24-hour event, so it's our pleasure to have you at your convenience as well.
Yeah, no problem. Thank
you.
This is David. Who is going to talk when we start? Is that Mohammed? And he's who will be the first speaker when we start again?
Yes, I think Professor Muhammad should present. He told me that he will be able maybe just to join.
Okay. Okay, he's traveling and he sent a copy of his presentation. If he can't make it, I'll do for him. Yeah, so won't interrupt your flow. Thank you.
Thank you.
I hope he will make it.
Yes, hopefully. Thank you so much.
Mhm. Hello, Isman. When should it start?
I think we need to start. I just trying to maybe give some time.
And
slides he sent it to me.
I got the slides. So who is going to talk? Are you going to talk about that, or you want me to do it?
No, of course you can do it. if
Yeah.
Mr. Muhammad will not be able to join, please.
Yeah, okay. So how much time do I have for him?
Maybe 25 minutes will be fine.
Oh, okay. So I'll start the talk, and then if he comes, and then you interrupt me, and he will take over. How about that? So we keep the everything flow. Is that right?
Yes, sure.
Okay. So as you can see, his okay. You have shown his bio already, and Mohammed he's a project manager at the Ministry of Science and Technology over the years, and he has completed. Should we record this?
We already record.
Oh, we already record. Okay, so he has successfully managed more than 30 national and international projects, and he is the director of Computer Society in Asia Pacific. And I have always admired his energy and his contribution, who keeps all the team together. Okay, so I'll just go slow with that. So this is region 10, and then under Mohammed Revdin, we have about all the regional directors. I'm in charge of Australia, New Zealand, and then Noble in charge, northern section, and as we know, the section, region 10 is going to be split into region 10 and 11. And so Mohammed and we are working very hard. We'll still be part of the IEEE family, but we also would like to use this opportunity to strengthen the ties between northern and the southern regions. So we can continue to work, collaborate even after that. So they are here's a list of all the Region 10 Computer Society chapters, and they are Australia and New Zealand. I have been visiting them and talking to them, and the Computer Society is very, those chapters are very active, especially in India and Pakistan, and then so they have a lot of create a lot of activities, and we have meetings every month, so everyone attends. Despite the time differences, the Indian time in the afternoon, and it was about 1 o'clock in the morning in Australia. So my wife always say, "Who is calling you?" Because Muhammad, I told him, always remind me, wake me up. So he is very good. So we set up goals and yeah, and just can you pause the recording for 1 minute? I think Muhammad. Hello, Muhammad. Yeah, you're online. Yeah. Okay, thank you. So we have improved information structure, chapter officers data, and then we we have been monitoring a lot of chapters to make sure their activities are reported through the V tools, and then that's quite important. And we do have some challenges, in terms of my area. I can only talk about it. I'm sure the other area, the regions, they're doing that really well. If they don't update that, I actually travel to go there. I went to Melbourne and Queensland. So can I talk to you? And we'll have a dinner, we'll have a lunch, and then things were done by that. And then we have managed project funding, and there are some statistics is coming up soon. Okay, the chapters meeting, in-person's meeting, and then we have that once a year, and then I'll show you some photos in the next few slides. And then we have leaders meetings and student chapter meetings. And one of another very successful event is the summer school. There's takes a lot of time to organize that, but it was well attended. And then here we would like to thank the headquarters for supporting us by providing fundings and all so on and so forth. Okay, so the next one we'll talk about continuously with some details. The Region 10 Chapter Congress was held last year in Colombo, and then people from the headquarters and then chapter chairs. I'll show you some photos, and are attended. And having said that, the area coordinator and new student chapter meetings online. As I mentioned, summer school, the people in India and Pakistan and of course Sri Lanka and other places, they work very hard, and the monthly regional meeting with area coordinators, and it's very successful because we have constant contact with each other, and then by the time if some things needs to be improved, we'll talk about that, and then people will do that. Otherwise, it's really embarrassing. We'll meet face to face. Okay, I'll talk a little bit more about that. And this is the last year's Congress, and it was very well organized by Sri Lanka, the chapter in Sri Lanka. The event was a huge success, and you can see the participants. With those meetings, what we have is the regional director and also the area directors, plus all the chapter chairs, and of course we have support and from the HQ, and then we have people from HQ joining us. So this is some more. 2024 summer school, as I said, it looks like fairly straightforward, but this is takes a lot of effort, and we give a lot of we are the whole group are very thankful for the chapters in India and to organize that. The next one is that there are some more. You can see the some more photos, and then another event we have each year is the road show, and as you can see, the last photo, and it's very successful, attended by a lot of people. Okay, I hope time is okay, and the road show, and you can see all those events. So next, I'll show you some statistics.
I'd like maybe to just mention that Professor Adwan is here. So.
Oh, okay. Maybe he can take over. Yes.
No. I can't see his name. Hopefully he can hear us.
Okay.
Thank
that's
you.
why.
Thank you, Dr. David.
Would you like to take over?
Yeah, I'll just continue and finished.
Okay.
Okay. Thank you. Sorry for the delay. I just arrived.
No, thank you for the support. I know it's difficult, but you made it.
You made it.
Thank you, and good morning to everyone. Okay, I'll just continue from what Dr. David have stopped just now. So basically, this slide shows the chapter members in R10. So we have 8,441 professional members and 13,778 student members. So in total, we have 22,219. Majority of the members are coming from student members. And if you talk about number of chapters, professional, we have 43. Student chapters, we have 375. So the student chapters for this year alone, we have around 40. Actually, this data is as 31st of October. Last month, we have another 2 more chapters. So we have roughly 40 student chapters for 2024. So in terms of a membership, overall membership, so we have the top 3 chapters in the whole, I mean globally. So these are Kerala, Madras, and Bangalore chapters. And if you see the top 10 chapters, I mean globally, so we have 6 chapters in the top 10. Okay, after Bangalore is Tunisia, Tokyo, Beijing, Santa Clara, Hyderabad, Washington, and also UK. Okay. So, can you turn to Dr. David, can you move the slide to the next one? Okay. These are the chapter grants. So for last year, we had 52 applicants. And for this year, we have around 64 applicants. And I can see almost all the grants are finished. 8,000 for the professional and 8,000 for the students. Okay, because in R10, we carry on a lot of activities. So funding is one of the important criteria. So we hope for the coming years, the funding can be increased. If possible, double the funding. So we'll have more activities and we can get more members. So in funding, we have 2 types. One is the core funding given by IEEE. So if your chapter organizes more than 2 technical activities, then you'll be getting a US 200. And incentive funding is given by the CS chapter based on the performance of the chapters. So they have some criteria for the ranking. So the top 20 will get some amount, 450. And the next 30 will get another 100 USD. So this is on top of the 200 USD given by IEEE. Okay, next please.
Next one is right. However, before you finish, Muhammad, you have done a lot of work. You have planned a lot of activities for 2025 next year. Would you like to, summarize that for our audience?
Okay.
Yeah. Yes, please go ahead.
Yeah. Thank you, Dr. David. At least you remind the 2025. So I thought I only need to mention what we have for 2024, but it's good to mention that. So for 2025, we have arranged some activities. One of them is the Chapter Chairs Congress. So we plan to have it in Indonesia next year in February. Then we'll be having our summer school. We already had 2 summer school for last year and this year, so we'll continue. It's like an annual activity. And then thirdly, we'll have some innovative competition among the chapters to encourage more chapters to take part in these events. And of course, we'll have some other activities like the webinars, DVP events, and also we'll have our own website and LinkedIn. We'll update all the information in this. So we hope the members will always go to the website or the LinkedIn to see what are the latest activities or information. And if generally some of the issues we had, maybe Dr. David have mentioned, is like we need more funding. And as far as chapters, I think the only thing that we have to push the chapter chairs to update their activities, even though they are doing a lot of activities, but it's not updated in the VTools. I think that's the biggest challenge we are facing. So every month, the last 2 weeks also, we had some meeting and some notification to all the chapters, ask them to update the information in the VTools, so that we can still become one of the most active chapters in terms of the activities. So this we have to keep remind, and we hope by end of this December, this thing can be done. You don't need to wait until January next year, even though the closing date for reporting is until February, but we try to get it done by this December. So these are the roughly our plan. Of course, we also have this collaboration among the chapters, so that they can organize as one of the big activities. And also the other thing is for student chapters, we are also encouraging them to communicate with the section chapters, so that more integrated student activities can be done rather than doing in a silo. So this can be done in a group for a single state. They can get all the student chapters and jointly organize one single event, so that we also could get a bigger funding for this kind of event. So these are some of the things that we are planning for next year.
Oh, thank you. Okay, I'm looking at the time. We still have about 7 minutes, 6 or 7 minutes. I'll just want to say one thing and to back Muhammad up before I open the floor for questions. The regional chapter congress was very successful, and Muhammad was too modest to mention the regional congress in the previous year. He spent so much time organizing in KL. So what I want to say for next year, it is still in the progress. We haven't decided, and I will leave Muhammad to make the announcement, but it will happen in February. And here we would like all the chapter chairs to join us, and with the VTools, please push. We are pushing our chapter chairs, and then, for example, in New Zealand, I have been asking people, said if so and so is not doing it, why don't you take over? And then last but not least, and Muhammad worked very hard. We got a new deputy regional director from Japan, and thank you for doing all of that, Muhammad. And then I'll open the floor for questions. We have about 5 minutes.
Thank you. I may have a comment or something to say. It's not a question, but I'd like just to mention also Professor Muhammad is a part of the DVP because he's member of the DVP committee and he was DV. So it's really a pleasure to us to with his support, and he did the DVP roadshow in Region 10, and I think it was successful one. So it's really important also to have some collaboration between the regions, because I had the privilege to visit India last year and attended the All India SYB Congress, and I have met there for the first time in person Professor Muhammad, and it was really amazing experience for me. And by this way, we extend this kind of activity. So we did the first SYB Congress in Region 8 this year. See, so how to exchange our thoughts, our ideas, our experience. I truly believe that Region 10 is our role model, maybe with a huge amount of members and activities. So I truly appreciate all the activities in Region 10.
Thank you. I'll hand back to you.
Yeah, thank you. Thank you very much, Professor Islam and Dr. David. So I'd like to take the opportunity to thank you, and also we hope to work more harder for 2025. So the chapters will give the official announcement about the chapter congress. So I hope all the chapter chairs can attend this event for 2025.
Thank you.
Okay. Okay, if there's no question, I'll end the session. And thank you very much, Professor Islam. And
Thank you.
Dr. David Chen.
Thank you.
Thank you.
No, so I think it's time maybe to move to our next session, which should be moderated by Dr. Guan Das. Are you there, Doctor?
Yes, I'm here. Okay.
Thank you so much for your support.
All welcome. Anything for the Computer Society, David and other Ravidan, Professor Ravidan, they are really kind enough to get me back. Just hold on. Let me open the introduction. Good day. Hello, everyone. This is Dr. Das, and you will find the old affiliation of the affiliation with the Computer Society. I'm not the part of Karachi section anymore. I moved to the Victoria section. So currently I am the MDC chair for the Victoria section. And let's move towards the today's session. I want to introduce the Professor Ghana Hezer. He is the science chair professor and also the John Loynes chair as well. He is currently in the UNSW Sydney, and he is going to present the talk on the Line OS towards a truly secure operating system. He is a very renowned professor. Let me say a few words about him. Professor Ghana Hezer is the professor and John Lane Chair of Operating System at UNSW Sydney, where he leads the Trustworthy System Research Group. His research interests are in operating system, real-time system, security and safety. His research vision is completely changed to the cybersecurity game from playing catch-up with the attackers to systems that are provably secure and safe. And I think this is a state-of-the-art need of today's time. Everyone is basically wrangling with the cyber threats and all that. With his team, he is pioneered with the large-scale formal verification of system code, specifically the design and implementation of the formal verification of the SL4 microkernel. SL4 is now being used into the real-time world security and safety critical system, hires former company Open Kernel Labs and acquired by the General Dynamics in 2012, marked with the OKL4 microkernel, which shipped on the billions of mobile wireless chips and has been deployed onto the secure enclave of iOS. He presently serves as the chief scientist of the Neutrality and the chairman of the SL4 Foundation. Garnet is a fellow member of ACM and also the IEEE Engineer Australia, the Australian Academy of the Technology and Engineering, and the Royal Society of New South Wales. And he's a member of German Academy of the Science, Lopedin as well. He's also the ACM Distinguished Lecturer and IEEE Distinguished Visitor. So I introduce to all of you, Professor Ghana, the floor is yours.
Hello, thank you for this nice introduction and pleased to meet you. Let me share my slides. Why is that forced? It says my sharing is forced. Okay. You can see my slides?
Yes, good to go, Prof.
Okay, thank you. Well, welcome people from around the world and specifically the Region 10. And it's a pleasure to be here and talk about our work on provably dependable operating systems, in particular this new project, Lines operating system, which is less than a year old. So the background for this all is that cyber attacks are a real world problem everywhere. They shut down airports, they spy on you. There's been a case where attackers tried to blow up a petrochemical plant in Saudi Arabia and got only stopped, ironically, by a bug in their attack software. And it's widely recognized to be a problem, although not enough is really done about it. And what makes this a particularly serious problem is that cyber attacks are increasingly used by organized crime and state actors. So these are attackers with with massive resources. And organized crime obviously tries to extract money, whereas state actors use it for spying as well as economic blackmail, and could actually potentially use it to cripple an economy. So serious problem. Why? What's behind it? The core problem is complexity. Complexity is always the arch enemy of security, and our computer systems are way too complex for us to handle. There's a rule of thumb of software engineering that well-engineered code, and the majority of code is not well-engineered, has 1 to 5 flaws per 1,000 lines of code. And just to put that in perspective, just the Bluetooth protocol stack alone that runs in just about any wireless device you use, as well as your laptops, etc., is about 100,000 lines of code. So that means there's literally dozens of bugs in there. And if you look at the whole operating system, the Linux and Windows kernels, there are tens of millions of lines of code. So basically, that means there's literally thousands of bugs in there, and that means thousands of places where an attacker can leverage to get it to break into the system. And the standard approach to this is what's called patch and pray. So you have a code base with a large number of lines of code. There is lots of bugs in there. Someone finds an exploit and hacks the system, and then everyone scrambles around frantically to try to patch up this bug. And what you had is 10,000 unknown bugs, and then now you have one less unknown and one known bug, and you fix that. And then the system goes through maintenance, features are added, etc., and you're pretty much back to where you started. So this is fundamentally a losing proposition. And anyone who dreams AI to solve this problem is actually dreaming, because AI actually makes it worse. It helps the attacker more than the defender. So this is not the way to carry on. We need better ways to deal with this. And that has to be based on really principled, solid foundations for security. And the first step for that one, we did 15 years ago with the SEL4 microkernel. So this is an operating system microkernel. I tell a bit more what that means. And it was the first operating system kernel where we produced a mathematical proof of implementation correctness. So in a very strong sense, that kernel is bug-free. It means that there is an abstract model that represents what the kernel is supposed to do, and we have proof that the C code that implements that kernel is correct. In that sense, really very strongly bug-free. We extended that to down to the binary code that runs on the actual hardware. So this means we don't have to trust the compiler to do a right job. And the compiler itself is hundreds of thousands, if not millions of lines of code. So it must be expected to be buggy. So it's great to have that one out of the trusted computing base. And we also did further proofs that show that the abstract model for this kernel is actually a good one, in the sense that we can prove that it enforces the key critical security properties of confidentiality, integrity, and availability. And while there's now some other verified kernels around, almost all of them are toys, and none of them has this really comprehensive security verification story SEL4 has. SEL4 is also still the only verified operating system kernel with really fine-grained access control. So this is what you really need to reason about security in a system. Any system that's not based on capability doesn't take security serious, and you can quote me on that. Besides that, it's also the only protected mode real-time operating system that has undergone a complete and sound worst-case execution time analysis. So this is the solid foundation for reasoning about timeliness in hard real-time systems, and a lot of control systems, of course, are in that category, as well as aircraft, etc. And besides all that, it's the world's fastest microkernel, and I'll give you some indication why I claim that in a second. There's a few, the kernel is verified across the three main architectures, ARM, x86, and RISC-V. Although for x86, there's only the function correctness proof, not the other proofs. And for ARM 64-bit and RISC-V, the story is almost complete, except for the 64-bit ARM architecture, where the security proofs are still work in progress. There's a few things that have not been verified to the same degree of soundness. I won't dive into those, but flag them here just for truth in advertising. And of course, the other cool thing about SEO4 is it's open source, so everyone can use it and adopt it. So back to my claim about performance. This is work that's been done totally independent of us by researchers at Shanghai Jiao Tong University. We didn't even know about it. First thing I saw was when I saw the paper presented. They looked at the performance of several open source microkernels, SEO4, the Fiasco kernel, which is a similar, or also called L4E microkernel, a similar kind of system, and the Google Zircon. And they looked at IPC latency. So these are the cost of sending a message from one protection domain into another one. So because it's a latency, smaller is better. And they found that SEO4 is about a factor of 3 faster than Fiasco and about a factor of 9 faster than Google Zircon. That's quite an impressive gap. But even more interesting, they compare that to the minimal hardware costs you need to send a message from one domain to another. And on the hardware they investigated, that's 790 cycles. So that means on top of what the hardware forces you to spend, SEO4 only adds about 25% additional overhead for actually doing useful work, compared to the others where it's, in the case of Fiasco, it's a factor of 2.5, and in the case of Zircon, it's a factor of 9. So that means, okay, theoretically, there could be a kernel that is slightly faster than SEO4, but only slightly. You might be able to be about 5 or 10% faster. More is just not possible because it's limited by the hardware costs, which is sort of the speed of light here. So in that sense, I'm very confidently claiming that this is the world's fastest microkernel. Okay, another thing that sets SEO4 apart from a lot of other verified systems is that it's been designed from the beginning for real-world applications. That was very much a driver of the work from day one. And it's been used in real-world systems. There's a few examples here. So this is a secure communication device used by multiple armed forces in daily use. There was autonomous vehicles ported to run on SEO4 in the DARPA HACMS program. That helicopter you see here is a Boeing airframe, pretty dated airframe, which they convert for autonomous flight. And initially this ran on Linux, and the DARPA Red Team took about 2 weeks to completely own it. And in the end, the Boeing engineers themselves, we weren't allowed to even see the code because it's export controlled, converted it to run on SEO4, and that kept the hackers out. So that was a very constructive demonstration of the use of this. Space satellites have been built. It's used in critical infrastructure protection. And as of 2 months ago, there are cars, electric cars driving on the roads of China that have an SEO4-based operating system. So a real touchable consumer product that is protected by SEO4. So that's pretty cool. And DARPA was brave enough that 2 years ago, they took this little drone you see here, which was the research vehicle for the DARPA HACMS program, where we tried out things which then the Boeing engineers put on the real system. DARPA took that one to DEF CON, which is the huge hackers conference that runs annually in the US, and they offered this steal this drone challenge. So basically everyone could try to hack into this drone, and as the DARPA program manager tweeted, many tried to break through, but none succeeded. So that was a very tangible demonstration of the power of SEO4 in protecting critical systems. So that's a good side. Why is this not the end of it? Turns out there's some issues. And one is fundamentally that SEO4 is a microkernel. So what does that mean? A microkernel is part of an operating system and it's distinguished from so-called monolithic kernels like the Linux and Windows operating system kernel, in that the microkernel only contains code that really needs to execute in the hardware's privileged mode. Everything else that doesn't have to run at kernel privilege is not part of the microkernel. And this is key to really stripping it down to something really very small, which makes it possible to prove it correctly. There is no way Linux is ever going to be completely verified because it's just too big and complex, whereas with a microkernel, it's feasible. SEO4 is about 10,000 lines of code. So that basically was at the time the limit of what was achievable. And that means because the kernel only contains very minimal code that is needed to securely multiplex the hardware, any actual functionality runs outside the kernel in user mode as so-called servers. And the advantage is that these servers are normal user mode programs and protected from each other. So there is strong isolation between them, which means if one of them fails or gets hacked, the rest of the system can be protected against that failure. And so that itself allows you to build some security by design into the system by leveraging the isolation that's provided by the SEO4 microkernel, which basically guarantees that these individual servers are protected from each other. That's the good side. The downside is, besides being a small kernel, is that the kernel does not provide any useful functionality, nothing of what you normally expect from an operating system. And so basically it's bring your own file system and device drivers, etc., which of course is not a reasonable suggestion. So in that sense, we need to look at the microkernel as being the assembly language of operating systems. And just as you wouldn't be reasonably expected to write a web browser in assembly language, no one in their right mind would do that, you should not expect to use the microkernel directly. So you need an operating system on top. And so our experience of the first 10 or so years of SEO4 deployment is that, well, it's still unrivaled in its power and assurance, but it's turned out to be extremely difficult to really design systems well on SEO4. So our expectation was industry would build operating systems around SEO4 and make it usable for system developers. And it turns out this didn't really happen because it requires too much expertise. And this expertise is very rare outside my research group. And I have to say with great embarrassment that actually my group has contributed some bad designs as well that got published and adopted by people. And so the painful realization from all this is that a lot of people who tried to deploy SEO4 ended up producing train wrecks. And that's, of course, very painful. It hurts me thinking about this, and it definitely hurts the reputation of the technology. It's just difficult to use. So the takeaway from that one 2 years ago was, okay, we have to stop fooling around and really provide the SEO of the community of adopters with what they really need, which is an actual operating system based on SEO4 and an operating system that's easy to use and obviously open source, so it's easy to adopt and well designed, so it actually gets you the full benefit of SEO4. And this is what led us 2 years ago to starting to work on what's now called LionsOS. The name LionsOS is only about 9 months old and came out with the first release. So we released the first version of this in March this year. And it's a very fresh project. We basically started it about a year ago and some preliminary work over the preceding year or two. So how do you do a new operating system? Most people who do that, in particular in the microkernel world, just reinvent Unix. And to me, that's totally the wrong approach. Unix is 50 years old, well past its use by date. And we really need to, if we have built a system from scratch, we have the opportunity of doing it better. And this is what what LionsOS aims for. So the LionsOS design is driven from 3 main aims, which we set ourselves. The first one is sort of what I already mentioned, a practical, easy to use open source operating system that people can easily adopt. And to make this feasible for now, we restrict ourselves to the embedded IoT cyber-physical domain. So we're not trying to replace laptop operating systems or smartphone operating systems or cloud servers or anything like that. We stick for now to the embedded domain, which is where most critical systems really are and where SEL4 is mostly deployed so far. So that's aim number one. Aim number two is we aim to be the best performing microkernel-based operating system ever. Turns out that's not that hard to do because most of them unfortunately perform very poorly. And then the third one, and this is really making full use of SEL4, we aim to be the most secure operating system ever. So if you look at some of the consequences of these aims, the first one, that we restrict ourselves to the embedded domain, means that we can simplify the architecture of the system. And in particular, we can use what's called a static architecture, where the architecture, as you think of the system, which is a bunch of boxes that contain services, etc., and lines between them, that's how they interact. This is fixed at design time. That doesn't mean what's in those boxes is fixed, but the structure of the system is fixed at design time. And it can be very strongly geared towards the particular use case. The second one implies that the system must be really well designed. And I think we understand very well now. It took us a while to get there, but we now understand well how to do that. And the third one, of course, means that we want to do what we did with SEL4 and push that into the complete operating system, meaning to prove it correct and secure. So these are fairly challenging aims, but I think we will be able to do this in the next few years. And the reason is that I think we really understand now how to do it. And the how-to is driven by very strongly the good old engineering principle of KISS, keep it simple, stupid. That goes back to the 60s, was originally coined in the US Navy, apparently. And it's really something that should drive all engineering design. And outside computing, it actually does drive most engineering design. And that's why our engineering projects, by and large, are actually successful and work. Our bridges stay up, our high rises don't fall over, unlike in the software domain. And key reason why things are so unreliable in the software domain is that this principle gets largely ignored. And so the way we use it for Alliance OS is what I call radical simplicity. We use very fine-grained modularity. And again, modularity is, of course, an aspect of every good engineering design, except in computing, particularly in operating systems, it's largely ignored. And in particular, the modularity is driven by strict separation of concerns. Again, a well-established engineering design. A component should have a clear design purpose and do nothing more than that purpose. We support that by what's called an event-driven programming model. So this is very much for computer scientists. I won't go into the details of this, other than just saying that this very much simplifies the programming of system services inside Alliance OS. And the third one, and I have animation for that. Sorry, jumping ahead of my slides. So the fine-grained modularity and strict separation of concerns is a key enabler of simplicity in the system that helps us develop the system, but also will help us proving it correct. The event-driven programming model is, just simplifies programming. And the third one, the use case specific policies, is probably the strongest departure from classical operating system design. It basically means that an operating system tends to manages a number of resources, and it requires policies on how to manage those resources. And most operating systems, or almost all classically, try to achieve universality in their policies. So if you look at Linux or Windows, they're designed to adapt to use cases, but without changing the code. And that works sort of well to a degree. It means that inevitably you run into cases where the implemented policies are pathologic and behave really badly. And then you add more code to make the policy adapt to those previously pathological use cases, and you end up with a very massive driver of complexity. To me, this is the biggest driver of complexity and therefore insecurity, unreliability of existing operating systems, that they try to have these universal policies. So we go exactly the opposite way and really tailor our resource policies to the particular use case. And I'm not claiming that this is a sensible approach for general purpose computing like laptops or server farms, etc. But from anything I've seen, and I've been dealing with a lot of industry partners over the years, everything I've seen in the embedded space can be served with this model. And so this is why we're building Lines OS on top of it. And the thing is, how can you, if you have a system that's tailored for a particular use case, how can you adapt to a different use case? Well, it's by rewriting the policies. So the idea is by having these policies very tightly tailored to a particular use case, they become very simple. And if you need a different policy for a different use case, you just write another very simple policies. And our experience is, in most cases, these are a few dozen, maybe 100 lines of code. Huge simplification compared to the really complex things like the Linux schedule is thousands and thousands of lines of code, etc. We don't do this. And so in a way, we just take really the opposite approach of existing operating systems. In particular, it's not a Unix-like system. But that doesn't stop us from providing wrappers that make it look like a POSIX system, at least to the degree that's required in the embedded space. Okay, so how does this look like? It's based on SEO4, of course, because that's the really bulletproof foundation for the whole thing. And on top of that, we built our Lines operating system. It uses what's called the microkit, which is an abstraction layer that makes dealing with SEO4 easier and is again geared towards the embedded space. And then we have an operating system which consists of many modules. And I'm serious in this saying many, in the sense that even relatively simple systems, and I give an example in a few minutes, consists of at least a dozen different modules, and in non-trivial cases, it immediately gets to 50 or more. So a lot of different modules, but they're all very small and simple. And of course, they are isolated from each other by SEO4's guaranteed isolation. How does this work in practice? Well, let's look at networking. That's one of the core functionality of just about any operating system. So we have a network interface card, and that's the black box on the right. And that needs to be controlled by software in order to provide networking services to the system. And that's done by a component called the device driver. And so that's the software layer that directly interacts with the Ethernet hardware and mediates access to the rest of the system. And in Lines OS, this device driver has that's following the principle of separation of concern. It has one specific concern and not more, and that's to translate between a hardware-specific device interface. So this is what the huge data sheet from the manufacturers say about this Ethernet card, to a hardware-independent, simplified interface that's common to all Ethernet devices, and that's presented to the rest of the operating system. So it provides a minimal hardware abstraction. And that single concern makes the driver massively simpler, factor of 5 or 10 simpler than a device driver in Linux. And that makes it much easier to get it right. And so the device driver just basically translates the interface and still presents a now virtualized network card to the rest of the system. And then somehow the device has to be shared with multiple clients, because in general, in the system, you have multiple processes that try to do networking. And this is a separate concern, which is handled by a separate component, which we call the virtualizer. So it virtualizes the device further by presenting logically identical copies to each of the clients. So it does a multiplexing job. It also does other things to do with virtualization, in particular address translation between the virtual addresses of the clients and the physical I/O addresses used by the device. And on hardware where that's required, it may have to do cache maintenance to keep the application's view of memory consistent with the hardware's view. That's all part of the virtualization job, which is put into this virtualizer. And for Ethernet devices, we can simplify this further by splitting the virtualizer job into a separate component for receive traffic and transmit traffic. So we have a receive virtualizer and a transmit virtualizer. The transmit virtualizer, the receive virtualizer receives packets from the network card and identifies which client the packet belongs to and sends it on. And the transmit virtualizer does the opposite. It gets packets, output packets sent by the clients and sends it on to the NIC. And if the clients try to overload the network, there is more traffic than the network card can handle, then the transmit virtualizer has to monitor and manage that somehow. So it needs a policy for what's called traffic shaping. And this is the only place where this traffic shaping policy is implemented. It's part of the transmit virtualizer. Again, in an embedded system, you tend to clearly know what kind of policy you want, whether you want to privilege one client over another, or you want to share the network bandwidth fairly, etc. That's the specifics of the policy, which is implemented in this virtualizer. And in general, as I said, it's a few dozen lines of code. Very simple, because we keep it application specific. And then there is a separate component for handling broadcast requests. And then there may be copiers needed for security reasons to keep the client address spaces separate. I won't go into any detail of that, but basically the clients need to be protected from each other. And so some copying may be required here. And then the actual Internet protocol stack is no longer part of the overall operating system. It's a library linked against the client. So every client has its own copy. And that's good, because the IP stack itself tends to be very complex, and so far no one has proved one correct. And so we don't really want to trust it and to break isolation. And so it makes a lot of sense to just let every client have its own copy of it, which is then just a library. It's still logically part of the operating system, but it's not a separate component. It's a library that the client links against. And so we end up with a highly modularized system. In this case, there's 2, 4, 6, 8 modules, which in the Linux system are all part of the Linux kernel, all mangled together, whereas here they're clearly separated and isolated from each other with SEL4-based isolation. We can also have virtual machines in the system for legacy reuse, so a client can be a virtual machine for the rest of the operating system. There's no difference. It just looks like a normal client process. So the whole design is modularized based on the principle of strict separation of concerns. We can also reuse existing device drivers, and that's important because you don't want to have to rewrite every device driver from scratch. You probably want to do that for the ones that are really security or performance critical, but that's very few in a typical system. And so we provide the ability of just replacing a device driver by what's called a driver virtual machine, where we run a Linux system, a minimally configured Linux system that just wraps around a single device driver for that particular device, and drop that in, and the rest of the system again is unaware that this is not a native component but a virtual machine. So it's all very transparent. One component doesn't really need to know what the other's details are. Very strict modularity. And the system actually also, the same approach allows us to develop components in Linux where we have better debugging, etc. So the obvious question there now is, how can this possibly perform? Because modularity has a cost, in particular microkernel enforced module isolation has a cost, because there's these context switches required between the different processes. And depending on the hardware architecture, the cost of that is sort of between 0.2 and 1 microsecond. So that sounds small, but it could be it could be significant, and it could degrade the performance of the overall system. So let's look at some measurements of this. So we compare the performance of LionsOS with Linux. Linux, very mature, widely deployed system that's been highly optimized over the years, or so you would think. Now, its device driver for our test platform is 4,000 lines of code. And we compare that to LionsOS, where everything is written from scratch and kept simple according to our principles. So as I said, the Linux driver, 4,000 lines of code. The network driver for LionsOS is only 700 lines of code, and it's been written by a second-year student. While this was a pretty smart second-year student, it does show that it's not that hard. I don't expect a second-year student to write a Linux device driver and get it right. And this one, the student did right. It was not only a second-year student. She wrote this driver less than 18 months after she wrote her first program. So despite being a smart student, it clearly indicates it's not that difficult. And the whole network system in Linux is about 1 million lines of code. In LionsOS, we can do it in less than 2,000. It's probably closer to 1,000. And so the question is, how does this perform? So we do evaluate directly against Linux. So we have a Linux system where we have network devices in the kernel, including the IP stack, and the client that runs at user level. And we have a network generator that throws load at the system, and the Linux kernel hands the data to the client, and the client simply echoes it back and returns it through the network. And our load generator measures how much load the system can actually handle, and we compare that. And so we do the same thing for LionsOS. And the Linux system requires 2 context switches per packet because by default there's an idle thread running, and then when a packet comes in, the kernel switches to the client to deliver the packet there. The client sends it back to the network via the kernel, and the kernel after sending it down switches back to the idle thread. So 2 context switches. In our SEL4 system, the LionsOS system, it's because there's so many components, it requires many more context switches, and it turns out it takes up to 14 context switches for each packet. So 7 times as many as Linux. So this could be quite significant. Okay, so how does the performance look like? We see it here on the x-axis. We look at the applied load. So we vary the load we throw at the system from almost 0 up to the limit for which the device is designed, which is 1 gigabit per second. And we measure how much load can the system actually handle. So how much does come back from the system. And we get this nice green line for LionsOS, which is what you hope for, meaning whatever load we put on the system, LionsOS handles it and sends it back. Whereas Linux actually tops out at about 600, 650 megabits per second. It cannot handle the full load. It can handle just less than 2/3 of what the network card is designed for. And we see the reason why when we look at how much CPU time is used. Linux basically maxes out the CPU at about an applied load of 650 megabits per second, and therefore cannot handle anymore. Whereas the LionsOS system, even at the maximum load, only has 60% of CPU time. So it's, by a fair measurement, it's more than a factor of 2 faster than Linux, which is nice and impressive. So this is on unicore. Linux is optimized for multi-core, so maybe it's doing better there. So if we let it allow it to use all cores on the system, then we find, yes, it can handle the load. But if you look at the dashed yellow and blue lines, you see that they're high above the green lines, which present LionsOS. So Linux still uses far more CPU time than LionsOS does for the same job. So in that sense, we comprehensively outperform the highly optimized, or supposedly highly optimized Linux kernel with our LionsOS. And real reason why we do that, despite having the extra cost of these extra context switches, is simplicity wins. We really, by keeping out any code that's not really necessary and tailoring everything to the use case, we more than make up for the cost of the extra context switches and really totally outperform Linux. So this basically shows that the Lions OS design makes sense. We can really build a high performance operating system that way. And we can't only outperform any other microkernel based operating systems, at least on networking, we can even outperform Linux. And that's, to me, that was actually unexpected. I thought we'd get within about 10% of Linux. I didn't expect us to beat it so comprehensively. Where does the name come from? Some may have heard of John Lyons. If you go to the Wikipedia page, John Lyons, it tells you he was a professor at UNSW, so that's my institution. And he was famous for what's called the Lyons book. That was a line-by-line commentary of the Unix 6th edition source code done in the 70s. And many operating system experts around the world learned operating systems from this Lyons book. Here is Brian Carnigan, the creator of the C language, with his copy of the Lyons book. And on the left, you see the officially published version. It was originally a UNSW technical report, and its distribution was severely restricted until it finally got officially published about 25 years ago. So that's why we named the system Lions OS in honor of John Lyons. What's the status? As I said, we did a first release in March this year. We have funding secured to finish the job. So I'm very happy to say that we've got enough money to do this properly. And we are totally committed to do that within the next 3 years, including the verification. So we have networking and storage works well. We have a bunch of other devices that work well. We have this framework for using Linux device driver, and we have deployments. So if you go to the SEO4.systems website, you will see a footnote that shows that the system is running on Lions OS. And we also have a point of sales system demonstrator, which is really meant to be used as a template for people to take as a starting point and develop their embedded systems on top of it. And we work on verification. I'll talk about that in a minute. So this is our point of sales terminal, which we call the Kitty, which runs on Lions OS. We use it in the lab every day. You can swipe your card and pay for things from the store. And this is the architecture of it. So it has a whole bunch of components. The green ones are part of the Lions operating system. And on top of that, it runs a Python interpreter, and that's where the business logic of the system is implemented. And the cool thing is most of these components are very small. There are a few hundred lines of code, literally. So this is a list of all the components in the system. And you can see nothing is bigger than 1,000 lines of code. The biggest part is a coroutine library to give us a POSIX-like file system interface. And most components are well below 500 lines of code. So this is truly radical simplicity. The big things are libraries we imported. So there is LWIP, that's the IP stack, the network file system client for using storage across the network, and the virtual machine monitor for supporting virtual machines. These are much bigger, but we didn't write them. We adopted them from existing systems, and we may rewrite some of these in the future. Now, I was saying that we want a verified system. So what's the story here? Well, the idea is that verification of Lions OS is much simpler than most other systems because of its simplicity and fine-grained modularity. And we have some data that backs this up. So part is the programming model, which gives us very simple event handler components, and very importantly, strictly sequential code. Every component is simply strictly single-threaded. Concurrency is only between the components. And that makes verification inherently very much easier. It makes just development very much easier. We find that we've spent very little time on debugging the component logic because it's just easy to get it right. The fine-grained modularity means there's a lot of concurrency between those components, and there's somewhat complex protocols for components to interact. And these are easy to get wrong, but turns out we can use these, we can use automated tools for verifying those. So we already found that the MicroKit implementation itself can be verified with automatic tools, so-called SMT solvers. Our protocols can be verified very easily with another automated technique called model checking, and we've done that successfully. And so we know that we can get very far by using automatic proving techniques for verifying line size. And the place where this mostly matters is device drivers. The problem with device drivers is they are commodity devices. SEL4 was very hard to verify. It was all done manually, so-called interactive theorem proving, and took about 10, 11 person years to do it. So that's a very significant cost. It's justified because SEL4 is a piece of infrastructure which is highly reusable. Device drivers are the opposite of that. Whenever you get a new device, a new SoC or a new processor board, it has new devices, and you need device drivers for them. And that means that driver development must be cheap. And that's also a reason why drivers are actually very buggy, because industry really cuts corners there. So we need a cheap process for not only developing device drivers, we already have that in Lions OS because they are so simple, but also to verify them. And the challenge here is that device drivers are written in a low-level language, and usually C, which of course has its problem in making it very easy to write the buggy code. And that would be, the drivers would be much less buggy if we had a better language. So we're looking for a programming language that makes it easy to implement device drivers, but it also supports verification, in particular with automated tools. And that's the simplicity we have from the Lions OS design. And so we now need the language to do the rest. And this language we come up with is what's called Pancake. So the obvious question people will ask is, why not use Rust? Because Rust is very popular, very trendy in the systems community. It's definitely a much better tool than C, but the problem is, and it does have strong type safety, which prevents a lot of bugs. That's why it's much better than C. But the problem is that it has no agreed semantics, and therefore it's not really possible to reason about Rust programs. People are working on verifying Rust programs, but as long as there's no agreed semantics, these are building castles on sand. And the other thing is the Rust compiler is huge and complex and must be expected to have lots of bugs. And the third one is that by interfacing to hardware directly, you can't do that in Rust. It violates the type system, and then you have the so-called unsafe escapes, and that defeats any verification. So while Rust is better than C in general, for us, it's not a solution. We need a better language, and this is our Pancake language. And Pancake is a very simple C-like language. And the cool thing for it is that it has a verified compiler. So we know we can trust the Pancake compiler. It will always generate correct binaries. And we can do that for verifying Lions OS code. And we've done that, and just a week or two ago, we formally verified the first device driver for an Ethernet device using this pancake language. And that's a real breakthrough, because so far, people have been working on device driver verification for probably 10 years or so. So far, no one has succeeded in verifying a device driver for a realistic, complex device like an Ethernet card. We just did it, and it performs. It still outperforms Linux. So that's sort of core for our LionsOS verification story, which is summarized on this slide, which is my last slide. So we have underneath the SEL4 kernel, which has been verified using interactive theorem proving. And on top of that, we have this microkit abstraction layer that has also been verified using automated theorem proving, SMT solvers. And now we're working on verifying LionsOS components using SMT solvers, and we already have demonstrated in a number of cases, including this Ethernet driver, that this actually works, particularly with the help of this pancake language. And then there's also the story that it's not enough to verify the components individually. We need to verify their interaction. And we have shown that we can use model checking very easily for verifying the inter-component interactions. And the ultimate goal, which we hope to achieve in the next 3 years, is to prove security and safety of the complete Lions operating system. This will still require a fair bit of research. There's a whole number of open problems there, but the team is confident that we will be able to achieve that. And core to making this achievable is the design of the LionsOS with the strict modularity and the fact that all the individual components are strictly sequential and all the concurrency is in direct interaction between those components. So in that sense, the concurrency is very strongly tamed in LionsOS, and that makes verification feasible. So stay tuned. Hopefully within the next 3 years, I'll be able to report that it's done. We already have the start of a usable operating system with LionsOS. There's a new release likely to happen before Christmas. And so it's growing and it's becoming more useful. We're building tools around it, etc. And so with having a fully usable LionsOS is only about less than a year away, I would say, and a verified one, as I said, 3 years. So with that, I'm done, and I'm very happy to answer any questions.
Thank you so much, Professor Garnet. This was really, really amazing and eye-blowing things that are happening from the operating system point of view. And hopefully we will be seeing this new operating system marketizing very soon. So the house is open for question. If you have any question, you are welcome to ask on the mic or on the chat. Or you can connect offline with Professor Garner if you have any additional queries on that. Check anything on the chat. All good. I think there is no question. Maybe you can connect with Professor later on offline. And it's thank you so much, Pro, for a wonderful, fabulous technical presentation. And it was really amazing to see all the incredible research that is going on into the operating system. Thank you so much. Thank you. Thank you.
Pleasure. Have fun.
Over to you, David.
Yes. Hi, thanks. Very, very good. I think we should follow the schedule. Start at 2 o'clock, right?
So we have 7 more minutes. Meanwhile,
Yeah.
people can
Yeah.
get their coffee or their meal, their
Yeah.
lunch,
And a
wherever
coffee.
you are.
Yeah. We'll start right on time, and yes, I can see Professor Chuck Brabati is here already.
Yeah, I am there, so I can wait for maybe for the next 5-6 minutes, and
Yeah.
then I am
So
trying to.
who is going to be moderating this? I'm just this one, and then is Minnie is going to moderate.
I'm here, David. I'm here. Hello.
Yeah. Okay, so you will do the monitoring, right?
Sure. I'll do this.
Yeah. Okay. So yeah, we'll start at 2 o'clock. I'm just wondering who is going to moderate the next slot? Is that it? Because on the schedule, my name is listed as the moderator. They must be. Yeah. How are you? Yeah. I'm just trying to, when we are waiting, we still have 5 minutes to go. Okay. My question is, according to this schedule, they asked me to moderate this. So this must be a change now. Yeah. Okay. You go ahead. Yeah.
Thank you, David. Thank you. See you. Bye-bye.
Islam, are you there?
Yes, Dr. David, I'm there.
Oh, okay. I'm just wondering which slot I should moderate.
Yes, according to the program, you should moderate the next session, not this one,
Okay.
but
Okay, the
from
next one.
4 a.m. Yeah.
So I'm only could moderate one session, right?
Yes, exactly.
Okay. Yeah, that's okay. Yeah, because the information I got a bit confusing. Okay, thank you. So that's
Thank you.
keep that. I'll take a photo of this. That's good. Okay, thank you.
Professor Islam, can we start now?
Yes, please, Dr. Romani, you can start. Thank you.
Yeah, I hope Professor Amlan is also ready. Professor Amlan, if you are ready, we can start.
Yeah, I am perfectly fine. Now we can start.
Okay,
Yeah.
thank you,
Sure.
thank you,
Go
thank
ahead.
you. So good day to all, and let me just thank Professor Islam for taking a lead in making this even again happen this year also. And thanks all the moderators and the fellow speakers. Good day to all once again. And now we have an excellent speaker for this next slot. I have great privilege in introducing Dr. Amlan Chakravarti, who is a full professor in the A.K. Chowdhury School of Information Technology, University of Kolkata. He's an MTech from the University of Kolkata and his doctoral research from Indian Statistical Institute, Kolkata. He was a postdoctoral fellow at the School of Engineering, Princeton University during 2011-12, and he is a recipient of prestigious Department of Science and Technology, Government of India Boycott Fellowship in Engineering Science in 2011, Indian National Science Academy INSA Visiting Fellowship in 2014, Japan Society for Promotion of Science, that is JSPS Invitation Research Award in 2016, Erasmus Mundus Learners Awards from European Union, and Hamid Visiting Professorship from the University of Cambridge, and Shiksha Ratna Award by Department of Higher Education, Government of West Bengal in 2018. He has also served in various capacities in higher education organizations, both at national and international level. He has also received multiple project grants in the area of security in cyber physical systems, embedded system design, VLSI design, quantum computing, computer vision, data science from various national and international agencies like the DST, DRDO, METI, UGC, DAE, and the list goes on. He is a senior member of IEEE ACM as a distinguished speaker, secretary of IEEE CEDA India chapter, Vice President of Data Science Society, and a life member of CSI India. I am also happy to inform you that he has been voluntarily contributing to the past 2 summer schools conducted by Arten also. So a very warm welcome to Professor Amlan, and we are looking forward to your talk on quantum computing, a revolution in problem solving. Over to you, Professor Amlan.
Yeah, thank you. Thank you, Minnie. And as you know that we are all volunteers of IEEE. And obviously that means once I joined IEEE and I just tried to focus that means how best I can contribute to the IEEE. Whenever something comes from IEEE, I am the first to go ahead with that. And thanks for inviting me in this very prestigious session. And so welcome my colleagues of this IEEE DVP event. And again, thanks to IEEE and IEEE Computer Society for inviting me. So today's lecture will be obviously something which is I think now coming in a very strong way, right, in every research domain, and and that's why. But when I started research in this domain, I think it was a really a very skewed domain. Okay, but now I think this is going a very strong quantum computing. Right, so many of the research labs started doing research, and many of big industries have also started their research in quantum computing. And so I think that I will try to motivate the audience of the real fun in quantum computing, especially how we can use quantum computing in solving some of the problems like optimization, machine learning, and the generic algorithms. Although having said that, quantum computing is obviously now not only a topic or a subject, it is now emerging as a stream. So it is very difficult to get into quantum computing and to make everything done in quantum computing of my 1 hour lecture. But I will try to give you some of the very interesting highlights of this domain. And I hope that this will create enough interest among you. Okay. So the way I will start is that, basically I will give a little bit basics, basic quantum computing, and then I will go into the domains of the different ways I can use the quantum computing, and I will just skip the research of University of Calcutta, but some of the activities what we are doing at University of Calcutta for quantum computing, I will also come up with that. Okay. So this is what is the roadmap of the computing systems. We had a fantastic talk before this, right, where we had a lot of the latest techniques in operating systems and system design. Okay, that is what I'm trying to pitch here is that this is the migration of our computer system, okay, from the early electromechanical quantum computing, which was basically relay-based quantum computing, right? We moved into the age of silicon, which is the present age, and it is fantastic, right? Silicon has gone to the miniaturization, and from VLSI to ultra-scale VLSI, okay, from 450 nanometer to 3 nanometer technology or 1.5 nanometer technology is really fantastic, right? And integration is going at a really at a very high scale, and we are having from the multi-core designs to chiplets, okay, which is amazing. But obviously, when we are crossing this particular, when we are traveling this particular roadmap, right, we are hitting device dimensions which are already some atomic layer depth. Okay, we are already hitting the atomic layers. Okay, so when quantum computing, that means we can say there are a lot of history about quantum computing. But if we go back to the most prominent one, the Richard Feynman's talk, right, I think in MIT. Where he spoke that means if we want to understand the quantum physics of the quantum world, right, we require quantum computers, okay, which can actually implement the quantum postulates. We have the systems which implements the quantum postulates, okay. So that's the direction. So we have the atomic states and subatomic states of our matter, which shows this quantum mechanical property, which are not very visible when we have the bulk matter consideration, okay, where we have a lot of atoms, a lot of molecules make some matter, but instead of if we just work on like a few atoms, right, or few molecules, okay, we can get into this quantum states, and hey, then we can use these quantum states to computing, and that's the beauty of quantum computing, and that's where the quantum computing starts, right? Whether we can use the quantum mechanical phenomenon which is inherent in this state of matter, we can design memory, we can design the state update of the systems, state update which is obviously computing, right? And can we have a proper readout where we can have an interface with the real world of the data, okay? Right. Obviously, what are the benefits of this? Obviously, we show that there are certain advantages in the quantum mechanical principles, which makes the computing pretty fast. Okay, obviously, if we can explore it properly, if we can leverage them properly, right? Having said that, it is not a thumb rule that every computing will be faster in quantum computing. Okay, it's not like that, but there are certain algorithms, there are certain problem domains where we can leverage the quantum mechanical principles, which I will give a little bit illustrations in this lecture, right? And that will obviously supersede the classical computing. And obviously these are very low energy computing, that if we can do it ideally. So obviously there will be a lot of energy savings, okay, if we can come up with some advanced quantum computing systems, right? It has promises to also give us a lower energy of operations, okay? So I'm not getting into this. So this is what is physically a quantum computer, a prototype looks like, okay? On the right hand side, this is mostly similar to an IBM quantum machine, right? But the quantum chip, okay, let me use a pointer, okay. Why am I not getting this pointer? Okay, so if we go to that extreme bottom of this particular system, right? This is where the quantum chip sits, right? And there are a lot of connectivities because these are the controls. These are the controls which controls the qubit operations, right? We have to understand when we get into the quantum system, we will understand that the qubit operations are pretty different from the normal computing pipeline, what we are actually presently accustomed with in our normal processing chips. Okay. And to control these qubits, we require a lot of cool temperature. So there is a cryogenic sealing of this because we cannot have the external thermal disturbances affecting these qubit states. So we need to cool them down at least of the order of 4 Kelvin. Obviously, this is a particular type of quantum computer. It means it's a superconducting quantum computer. It doesn't mean that every quantum computer might be requiring that. And that's also the research which is going on in quantum technology, that what are the different types of technologies we can have in quantum computing. But I am just trying to showcase one particular thing, right? And this that means all this bunch of words are just to give the proper signals, because here the computing means that you are updating the qubit states, and the qubit states are updated by the signals, which are again controlled by a controller, which can be in your classical world, okay? So the phenomena for the quantum computers utilizes are superposition, entanglement, and interference, and I will try to show this in a very specific way, that how it helps in computing. So obviously there are a lot of hypes in quantum computing, and obviously we are looking forward, being a very optimistic quantum computing scientist. Okay, almost over 20 years, right. I want to see this progress of this quantum computers. Okay, and many of us will be really looking forward to that. That means what is the new quantum computer coming up, right, in the next year or the next. Okay, so obviously there is in the 1,000 qubit quantum computer, right, which has been announced by a distributed QPE system from IBM, right. Obviously is making a lot of what I can say, that means it is obviously a big impact in the quantum computing domain. Now, if we go into the little bit more depth, right, what makes this quantum computer, if we try to compare the quantum computing with the classical computing in some of the performance metrics, okay, what we try to, what we can leverage out of the quantum computer, and what are still the limiting factors of quantum computers, okay? So obviously, if we go to the computing resource, the computing capability of a quantum computer compared to a classical computer, okay, we will obviously see that the resources to computation, okay, is obviously exponential in the quantum computing domain, which means that suppose I give you n qubits of resource, how much data processing you can do, okay, in the quantum computing. Okay, if we have n bits of quantum systems, which is called a qubit, n qubit quantum system, we can maximally go up to a range of 2 to the power n basis quantum states. Okay, and each of these n basis quantum states can encode a particular data point of your data space. So what I actually mean is that with an n qubit quantum system, I can process a 2 to the power n space of data. Right? In the case of classical, it's linear. If you have an n-bit register, you can process an n-bit data. Okay, that's the power. That's the first power of quantum computer. Okay, right? And obviously, okay. Sorry, I missed it. The first point, that is the basic computing units. Okay, the basic computing units in a quantum computer is called qubits, which are called quantum bits. Okay, right. In classical, we know it's called bits. Okay, so the difference between a quantum computer, the quantum bits and classical bits. The quantum bits have some phenomenon which are not present in classical. Okay, that obviously a classical bit can be always set to 0 and 1. Right, whereas the quantum bit is a 0 and 1 are two extreme states of quantum. Okay, a quantum bit can exist in states. Okay, which can be decomposed into 0 and 1, which means that it has several possible states. Okay, a qubit can be in several possible states, and only 0 and 1 are the two definite quantum states. Definite values what the qubits can attain, but it can also attain the certain values which are between the 0 and 1, or which has probabilities, which are some probabilities of 0 and some probabilities of 1. And this large number of states actually generates this superposition of the qubits, and that's why the computing capacity is so large. So we can have ideally we can have an n qubit can generate 2 to the power n superposed basis states, right? And that's what's the computing capacity. So the basic phenomenon of qubits in superposition gives you an enhanced capacity in computing. But obviously the question is that whether we can utilize that capacity or how we can utilize the capacity of this. And that is obviously the challenge we have to take care when we try to put an algorithm in execution on a quantum computer. So on that also there is one obviously concern, which is error. Because what I am telling is an ideal quantum, okay?
It's 200 Australian dollars, right?
Hello. Yeah, is there anything coming up? Okay. So there are errors, and these errors will actually change the distribution of the basis states. Okay, these errors are basically interaction of the quantum system with the external world, right? And these interactions can actually oscillate the qubit states, which are unexpected. And this oscillation of the qubit states can generate a different distribution on the basis states, okay, which were not defined by the computing what we have performed. And that is obviously a concern of error. And the thing is that more and more we go into the number of qubits, okay, the error increases almost exponentially, as well as more and more we go into the depth of the circuit of the quantum operations, means how many quantum operations we are performing on the qubit states, right? The error grows up. So this is actually both ways. If we try to spread, right, either vertically in terms of the qubits, right, or horizontally in terms of quantum operations, our error grows up. Okay, right, and that is obviously a concern. A lot of technologies and a lot of thought processes are going on. Okay, in this how to reduce error, and that obviously if we have large number of qubits, if possible, we can actually go to the fault tolerant quantum computing, like okay, that utilizing the error encoding. Okay, which is called the FTQC type of quantum computing, but we are not at that particular level at present, because at present we don't have enough number of qubits to implement the FTQC, because the qubits will be utilized mostly for data encoding due to the less number of qubits. Okay, so at the present scenario, obviously we can only go for smaller scope of our computing, right? Okay, and those are really the issues which you have to take care. Okay, and the last point is the suitability of quantum computing. So as I said, that obviously quantum computing is exciting. Quantum computing has certain things you can do in quantum computer which you cannot do in classical computer. But it is not just a mapping, okay, from a classical to quantum. You cannot do that. Okay. So you have to have the particular recipes in your algorithm to exploit the quantum computing, okay? And that's why it's called the quantumness of the algorithm, okay? So we have to study the quantumness of a given computing algorithm, and then only we can actually look into its quantum computing design or implementation. And that's why there is a sort of thought to be taken care of, like a suitability of an instead of classical, if we do quantum, what is the quantum supremacy? We call the term called quantum supremacy, which means that, hey, the quantum computer performs much better than a classical computer. So just going to the fundamentals, okay? So So this is what is a very simple analogy of a classical computer vis-a-vis classical bits, okay? Okay, vis-a-vis quantum computing bits, okay? Classical bits and quantum computing bits, okay? So this is on the left. What I show is the classical bit, which is two steps of zeros and one, okay? And we have a quantum computer, quantum qubit, which is shown as a qubit state on a block sphere. Okay, this I will come very soon, but just to get it that, okay, this is a representation of the qubit state, okay, a single qubit state. So, okay, as I see that in the classical, obviously there are only two possible states of the switch, okay? Either you make it on or you make it off. Whereas in a quantum computer, right, obviously 0 and 1 are the two extreme states. Okay? One is on this axis of the block sphere is called the z-axis. These are the two extremes of the z-axis, okay, 0 and 1. But obviously the qubit state, which is represented as a vector in this block sphere, can be at any point on the surface. Okay? And something on any point on the surface obviously can be projected okay, in the 0 and 1, but with certain probability. So the actual state is not exactly 0 or exactly 1. It has certain probabilities of that. Okay, once we project this vector to 0 or 1, we will have certain measurements of the qubits, and that is the probability of the qubit to getting measured at 0 and 1. So this is completely a different type of different type of data understanding. Okay, that means or the state understanding vis-a-vis a classical and quantum. So in a classical, the states are definite. Okay, either you have a 0 or you have a 1. Right? In a quantum, or the qubit states are probabilistic, means every state has a probability to get measured into the 0 basis with some probability, and right, and with a 1 basis with some probability for a single qubit. For a single qubit, we have 2 basis states, 0 and 1. Okay, right, and these basis states will go on increasing 2 to the power n once we increase the number of qubits, and then the probability space becomes a very large sample space. Okay. Okay, this is a little bit more look into this qubit state. So as I said, okay, this is a Bloch sphere. Okay, this comes from the quantum mechanical solution of the quantum system. I'm not getting into this solution, but you can get into okay, this understanding. Okay, right. What this sphere is? This is a unit radius sphere. Okay, this is a 3-dimensional space. Okay, unit sphere. So it has 3 axes, X, Y, and Z. Okay, the Z axis is one of the very common axes, which is marked, right? And 2 extreme points of the Z axis is 0 and 1, right? And obviously we have the X axis and Y axis also. Okay, so a vector which I show here is a psi. So psi, you show a little bit angular brace here. So this is called a Ket notation, and this comes from the quantum physics. So when we show a particular value in a classical system, we don't use this Ket, okay? But when I tell to say that, hey, this is a quantum state, okay, I will use the Ket notation, which identifies that this particular state is a quantum state, okay? Right, and if we see this, a quantum state is represented in the Bloch sphere as a vector, okay? So this is the blue line is the vector of the quantum state, okay? Is a vector representation of the quantum state, right? And this vector has different projections based on which particular axis you measure the vector. And this is also a very good tool to encode the data. So your data so exact value of the vector of the qubit state only doesn't depends on the particular position of the vector, but it also depends on the axis on which you measure the vector. Okay, so that is so important. Okay, and the operations on the qubits. What is the operation of the qubits? The operation of the qubits are nothing but changing the orientation of the vector in the Bloch sphere. So the operation can be moving the qubit state, moving the vector from here to here, which is equivalent to a different probability of the qubit state measured across z-axis or x-axis or y-axis. Generally, we do measurement across z and x. We don't do the measurement across y-axis. Okay, so this is the beauty of the quantum state. So the update of the quantum system for a single qubit, for a very smallest quantum system, which is a single qubit quantum system, means that you are changing the position of the vector, which means that you're coming to a different value of the psi, and this generates a different probability of measurement across the axis. So this is a nutshell, right? You can have more details of this, but again, I am just skipping a bit. Okay. Okay, as I said, that the measurement of the qubit depends on different axes. So there are X, Y, and Z axis. So this is also an uncertainty in terms of the data, and that is very, very well used in the distribution of the quantum information in the form of QKD. Okay, I'm not covering QKD here, but if you look into the QKD, which is now well applied also, okay, you will see that instead of making the randomness in the data, we also make the randomness in the basis, in the measurement, in the choice of the measurement of the data, okay, of the photonic pulses. Okay, so as I said, okay, now what is a quantum operation? Okay, so computing means you update the data. Okay, obviously it should be a controlled update of data, right? As per your computing logic, you update the data, and then what you can tell it's a feasible computing. Similarly, what I show here is that, hey, you can update the qubit state, okay? You can update the qubit state by single qubit operations like rotation gets. Okay, this rotation gets, suppose this is a very, very toy example where I show that my qubit state was here and I rotated it across the z-axis, okay, and it came, the qubit state becomes here, so which means the vector rotated, okay? The vector rotated generated a new quantum state, and this new quantum state, if I measure across the z-axis, we'll have a new probability of 0 and 1, because if I measure this probability here, it is absolute probability 1 for 0, and 0 for the state 1. But if I measure the probability here, this will have some probability of 0, obviously a larger probability of 0 and a smaller probability of 1. But still, the probability got different, the probability got changed, right? And the probability got changed means the qubit state got changed. Okay, and that is what is the computing. Okay, so computing here means the data update means that you are trying to update the qubit state. Okay. Right, and this is a single qubit operation, and this single qubit operation can be fundamentally, obviously we can do many logical operations, but we have to understand that, like a VLSI also, okay, we have some primitive operations supported by technology. Similarly, there are some primitive operations supported in the quantum system, which are the rotation across X, across Y, across Z axis, and these are called Pauli gates. Right, and any single qubit operation, any operation can be decomposed in terms of this particular case, and that is the key idea of how to update a qubit state. Okay, I'm just skipping at a bit, and this gives you a little bit hint towards how we can approach the distribution problems. Okay, that means you have a search space. Right, you have to map the distribution of the search space, and the system and your computing system have to understand the distribution of the search space. Okay, right, it can be very, very well used in optimization problems or in machine learning also. So what I show here is that, hey, my quantum system can generate distribution. A single qubit quantum system can generate certain distributions. Okay, and this is an example, right? Obviously, this example shows it's a 50-50 distribution of your high and low, which means that it is a very well-balanced distribution. But we can always tweak the distribution. We can always tweak the distribution with some initial bias on the quantum state, with some more operations on the quantum state, and I can tweak the distribution. Okay, then instead of 50-50 distribution of 0 and 1, we can make a 60-40 distribution of 0 and 1, depending on where I am taking the vector, where I'm moving the vector. Okay, so this is really wonderful, and this is the way how we do the quantum updates. Okay, okay, right, and then I go to the very simple understanding of this particular phenomenon, which is called the quantum phenomenon of superposition and entanglement. Okay, so what I show here is the first example. What I show here is called a superposition. So superposition means that, okay, that means, as I said, that n qubit system can generate a 2 to the power n basis distribution. And that is what is shown here. Now, each of the bases comes with its amplitude. So now each of the bases can be used for encoding a data point in your data space, right? And the corresponding value of the data space will be scaled with the amplitude of the basis state. Okay, so in this way, we can actually encode a larger data space in the quantum domain using a smaller resource, because n qubit can encode a 2 to the power n data space. Okay, right. And then I show the entanglement. So what I show here is that the second the illustration. What I show here is that, okay, this is a qubit quantum system. Is very easily understood because it is right. It consists of basis states of 0, 0, 1, 0, 1, 1, 0, and 1, 1. And obviously, a 2 qubit quantum system can be decomposed into two distinct qubit states like this, like a tensor product of two distinct qubit states. And this is fine. This is not entanglement. This is a superposition. So any superposition states which doesn't have entanglement obviously can be decomposed into single qubit states. And a single qubit states with a tensor product can generate the entire distribution of the superposition over the basis. But the last example what I show, which is also a 2 qubit state because it has the basis of 0, 0, and 1, 1. But this particular state cannot be decomposed into 2 qubit state. You don't find the amplitudes A, B, C, D which can decompose this into 2-qubit states, which means that 2 qubits are so closely coupled that we cannot disintegrate these 2 qubits. Okay, and if you look into the state distribution is very unique here. Okay. Okay, normally a 2-qubit states will have all the probabilities of 0, 0, 0, 1, 1, 0, 1, 1. But instead of this, we have only the probabilities of 0, 0, and 1, 1, which means that 0, 1, and 1, 0 has vanished in the distribution. So this is disruptive distribution which happens in entanglement. So entanglement are basically forceful distributions, okay, in the quantum space, where we can single qubit operations can do certain distributions. You can use certain bias and do certain distributions, but you can make some stronger distributions using entanglement. Though entanglement are also used in communication, quantum communication for some other purpose. I'm not getting into that, but in quantum computing, okay, to generate disruptive distributions, we can use this entanglement, which means there is a definite operations called Bell state operations between the qubits, which generate this type of distributions, which are very unique. Okay. I come to the closer of this particular part where I say that what are the things, okay, if I compare between the classical and quantum, okay, obviously the classical have the gates, which are already known, and the quantum have single qubit gates and the entangling, okay, 2-qubit gates. Though these are the primitive quantum operations, when you go to the logical quantum operations, obviously you can have a larger gates, okay, but ultimately all the quantum operations in the logical level will be decomposed into the single qubit and this 2-qubit operations, okay, at present in the technology space, right? And this is a classical quantum circuit, how it looks like, right, in the IBM Qiskit tool. Okay, so the way if we try to understand this, here, these zeros to Q1 and Q2, these are the qubit states. Okay, right, and right, and this is the way that means I initialize. Okay, so just to understand that when I tell psi, it means that Q0 is initialized with the superposition single qubit state, whereas Q1 and Q2 initialized with the qubit states as 0. Okay, right, and these are all the quantum gate operations. Now, one thing you have to be careful here is that the difference between a quantum, that means a quantum pipeline and classical pipeline, is that in the classical pipeline, the signal flows, okay? Signal flows from the input register to the output registers, right? And all the functions are being done in the space, okay? That means from the, okay, in the space we do. In the case of quantum, it is not an input register and then it goes to the output register. It is the same qubit register, right? And this axis, which is across the X, is a time axis, which means that the same qubit register is operated with the quantum transformations, with the quantum gate operations, and the qubit register gets transformed, get evolved, and that's why we call the quantum state evolution. Okay, so this is what is the basic difference between a classical pipeline and a quantum pipeline. So we have the same state, which starts with the same state with some sort of initial distribution, and we try to modulate the distribution with the quantum operations, okay, on the qubit system, and we try to evolve the qubit system from some initial state to the result state. Okay. Okay, so I think I have next 15 minutes. Okay, if you can help me. Okay, how much time I'm having from here?
Yeah, you have 25 minutes more.
Oh, 25 minutes more. Okay, so I'm very fine. Okay.
Yeah, 1 hour.
Okay, so now I'm coming to the problem solving part. Okay, so obviously the problem solving part, there are many things we can do in quantum computing. I take my lecture course right in university, right? But obviously the most attracting quantum, okay, the problem space, and right, and also the theme which matches okay with this particular event, right? Artificial intelligence, right? And okay. So machine learning obviously comes into this particular place very well. So what I will try to make you motivated that, hey, can we get something, okay, some leverage? Can we leverage quantum computing in machine learning? Okay, and that will be my discussion for the next maybe 15-20 minutes from here. Okay, so what is quantum machine learning? Is obviously machine learning. We know that machine learning is something that we try to extract the knowledge of the domain with some sort of learning model, right? And once the knowledge is abstracted, right, properly, we can actually build a decision system, right, which is supported by that learning of the domain, right? The decision system is called the inference engine, right? And once the inference engine, is properly done, we can actually use the inference engine for, we don't need to now learn. We can just use the inference engine, for your new data, and you can either take a decision of classification, or you can go for a prediction of some outcome. So so obviously the main focus of this machine learning is two things. First is understanding the domain, right? And to understand the domain, we actually go into the feature space. We try to look into the contributions of the features. Contributions of the features, in the domain, right? And this can be a supervised or unsupervised type of approach, right? And we try to right, and this features, these features, the strength of the features are analyzed by the present techniques like deep network. We use kernels, right? And also in the classical machine learning, also we used kernels. So the kernels are something which are something like filters, right? Which are mapped with with certain certain that means it captures the features. That means, and if the kernel results are high, we say that those features the features which the kernels generated higher values, those features are strong features in your things, and those are ultimately utilized more in the decision space, for the inference engine. And that's where we capture the knowledge. So we capture the knowledge in the domain by applying kernels, and we try to that we map the kernel outputs, right, and try to slowly take the kernel outputs to the decision point. Right. And in the case of quantum machine learning, what you try to do, we obviously have to do these operations, but these operations will not be done in the normal data space, but in the quantum encoded data space. And that is where the difference comes up. Let's try to look into this particular problem domain now. When we look into the quantum machine learning, or also called QML, we have actually, in general, we have four types of machine learning problem, considering the data and the computing environment, obviously. So we have the classical data and classical computing, which is obviously we are doing very good. Then we have the classical data and quantum computing, which means that we have to encode the classical data, right, into the quantum system in terms of a qubit distribution. And then we have to operate on the qubit distribution. And then we have to come up with a measurement of the qubit distribution and generate the classical outcome, right? And obviously, this is the most common quantum computing we are doing now, Now, quantum data and classical computing, which is in the lower half first quadrant, this is called simulation. This is called simulation. Means we are trying to simulate a quantum system in a classical. We did a lot. When I did my PhD, the quantum systems were not there. When I was a postdoc at Princeton, the quantum systems were just, we are listening that, hey, some quantum systems are coming up, So we did a lot of work, which were actually, and still we do, before realizing something in the quantum system, we have to estimate that whether the quantum system, quantum algorithm, can be evaluated in a small scale environment, in a simulated environment. And that simulation is obviously a classical, And then comes the quantum data and quantum computing, which is the rightmost bottom corner of this particular thing. So quantum computing, quantum data is something called that the source data is quantum, and obviously we can actually process it quantum mechanically. And there are things like quantum sensing, quantum metrology, where the essential data is actually the quantum data, right? And we are trying to generate certain inference out of those particular data which are being sensed. So there are a lot of things and a lot of options are there, right? And obviously a lot of domains are coming up, emerging, right? How we can use the quantum computing in what form, right? So, so now if we look into the advantage of quantum computers, is one of the advantage of quantum computers is that, it can obviously look into a larger data space, because it can encode a larger data space, as I said, n qubit can encode a 2 to the power n distribution. Okay. Secondly is the search criteria. So a search criteria in a data space means that, hey, you run the oracle on the every point of your data in the search space, whatever search space you have defined, right? And you try to find that. Okay, I mean, if there is only one solution of your problem, then in the search space it will find it. That means it will find the oracle or the cost function what you have done is minimized or maximized for that particular data point in your space. Okay. Now the challenge is that how to go to the data point. Okay. Okay, because in classically you have to do some sort of stepwise operation. Either you do a grid search, right, or you do a random search, right, so that you are trying to move into the data space and trying to find that, hey, which particular data point gives a minimum value of the function, right? So in quantum, what you can do in quantum, you actually can run this particular oracle on the entire data space, okay, concurrently. Okay, it's called a functional parallelism, which I haven't explicitly shown in this particular lecture, but you can do it, right? You can do a functional parallelism of, that means in the quantum space, which means that as you are generating a 2 to the power n space, okay, that means a basis spread of your data is now represented by 2 to the power n basis states for an n qubit system, right? And if you now apply a function, this function will be operating on the entire space because your states are in superposition. So if you apply a function on a superposed state, right, the function will be hitting all the states which are in superposition. And then the function will be also generating an outcome for all these superposed states, okay? And the outcome will also be in superposition. Okay, now this is obviously a challenge now, okay? That means in the classical, you come up with one outcome. Okay, in the quantum, you come up with an outcome which is also a distribution, right? And now how you take a particular outcome out of the distribution, which is obviously your choice. Okay, obviously there are certain ways to increase the probability of that outcome, okay, compared to the other outcomes. And then we measure after certain iterations of increasing the probability of that particular outcome. And that is fundamentally, can be done with an algorithm called called the amplitude amplification, where we can selectively amplify the output, selectively amplify the amplitude of a certain state compared to the other states. And then if we go on doing this, after certain iterations, the amplitude of that state will be quite high. And so if you measure a probabilistic system, okay, that means we will get that particular measurement higher probability than the all other values. Okay, so this is the way we try to do, and we have found that okay, the cost of actually doing the amplitude amplification in the quantum system compared to the classical search, where we have to span the space that means each step is each iteration in your span. Still, the quantum amplitude amplification gives you at least a polynomial, okay, at least a polynomial speed up compared to the classical. Okay, classically going into the every data points and searching it. So now when we apply a quantum mechanics, and now try to understand that you are applying the kernel, which is obviously a sort of search function, which is actually maximizing some data points and minimizing certain data points, can now be applied at one shot over the entire distribution, and the kernel operation can, the result of the kernel operation can come up, okay, with the entire data space as a distribution, right? And you can go on and on the kernel operations in your sequence, right? At a point of time, obviously you have to measure, and when you measure, you have to be very careful that, okay, that how we're going to measure this particular outcome, right? How we get the actual score of the entire feature space. Okay, so in order to do that, I said that the fundamental way of changing the quantum states is obviously the rotational operations, as you see, the single qubit operations and the 2 qubit entangled operations. So we have to parameterize these operations, just like the parameterizing the weights of the neural networks. We have to parameterize these operations And this is what is actually the learning. So the learning of a quantum circuit is basically to generate the parameters of its gate operations, of its quantum operations, such that the decision, the inference, what we want to, the distribution which favors my inference. Okay, if it is a supervised system, I know that what the inference would be. Okay, for a large number of data sets. Okay, data points. Sorry, a large number of data points. I know what will be the inference for each of the data points. So our that means our quantum challenge is that, hey, can we actually start with a distribution, favored distribution, and go to a distribution which is defined by your training data, right? And then if you want to map all the data points, all the inferences that are already existing in your training data, right? What will be the parameters of my gate operations so that I can generate those distributions which maps with my inference. And in order to do that, we need to have the parameterized quantum circuits, and these are all represented by this alpha, beta functions of the quantum circuits. Okay, so what I try to converge here is that, hey, so we now need to start with a distribution and go with a distribution, and we try to generate a distribution. Okay, and I instead of solving a particular problem of machine learning, what I show here is generically that really you can generate distributions. Okay, so what I show here, if I summarize this, I show that this is a 2-qubit space. And in a 2-qubit space, we have 4 states, 4 basis states, 0, 0, 0, 1, 1, 0, 1, 1, right? And I can show that I can generate a distribution which looks very good, okay? All having a 1/4 probability of getting, because we are making every qubit, okay, that means a very, okay, that means a non-biased state, okay? 2 qubits in non-biased states will generate a distribution which looks very good, okay? Okay, but obviously, if we try to use entanglement, different ways of doing entanglement, we can come from a distribution which is very uniform distribution, okay, a distribution which is very disruptive, and we can do it slowly. We can do it at our own control, right? We can generate distributions, right? And these distributions can be very well part of the distributions what your kernel functions generates, okay? And that is the entire quantum game, right? How you can define the quantum operations, which defines a quantum kernel, and which can actually take your feature space, okay, into the different distributions of estimations, okay? And that is what is the game of the quantum kernels or quantum machine learning, okay, right? So we have to use the single qubit operations with some entanglement operations to generate these distributed distributions and the varying distributions, okay? Right, I will skip this a bit, okay? So this is what is a quantum circuit, okay? A parameterized quantum circuit looks like, okay? So we have the states which are initialized here, and we have a sequence of the gates, okay? And then we have the measuring this qubit states again, and so we come with a distribution, okay, which we try to do it much better in the encrypting state. And we come up with a distribution which actually that means to generate our inference engine, and we have to settle down the things which are in between. In between, we have 2 qubits and single qubit gate operations. Okay, right? And so what I show here is that there are 2 types of quantum algorithms. This is called the first generation quantum algorithms, which I studied when I was doing my PhD. Very classical, very well defined algorithms like Shor's, Grover's, HHL, and something like this. Phase estimation, QFT. Very definite quantum algorithms. But now if you tell me that what are the quantum algorithms are interesting and coming up, and people are trying to use it, obviously these are all parameterized quantum algorithms. So which means that the U theta. So why did this come U? Because I didn't come to that mathematical descriptions, okay, to make the thing simpler. So all the quantum operations are unitary transforms, okay, in the vector space, okay, in a multi-dimensional vector space, okay. And so, right, and so we parameterize these operations as U, and we parameterize this with the theta. So theta are the parameters, okay? And so these are the algorithms, and these are the things we can, and this is the synthesis part of it, okay? So how with a big U theta, that, like, though you can generate a logical U theta, but you cannot implement a U theta. So to implement a U theta, you decompose it, and that's what a quantum synthesis problem. Okay, right? Decompose it, but decompositions also have certain constraints, right? You cannot just do decomposition blindly. There are certain constraints, both in the quantum domain and both in the technological domain we have to take care, right? And this is also quite a good amount of tasks to be done, okay? I'm just skipping it a bit. So these are the different types of ways we can encode the data. So as I said, that the feature space encoding here are the values what we can generate out of the qubits, distributions which can generate out of the qubits. So we have to orient our qubits, or we have to transform our qubits, okay, to represent the data space, okay, right, and that is called quantum encoding, okay, to implement or to take the classical data to a quantum domain, okay, right, and this is, and in some cases, or I can say in general cases, okay, the determining the theta for our circuit is not so easy. So we have to use certain sort of classical, certain optimizers, and we can use the classical. So many of the things which is something like the HPC, the hybrid quantum classical computing, which means that here the quantum computing actually in the training phase of quantum computing. In the training phase of quantum computer, we try to settle down all the parameters of the quantum computer using an optimizer in the classical system, and then we train this quantum system, settle the quantum system, then we try to then we freeze the quantum system, the pretend quantum model, and then we can run the quantum model for your data, for your new data. Okay, so this is the cycle what is followed in many of the quantum optimization domain. Okay, I'm just skipping it a bit again due to the time. So there are different types of decomposition techniques of the bigger U, right? How you decompose the bigger U into the horizontal, into the vertical, disjoint tensor operations, or into the product operations which are on horizontal, or you can club both of them together. Okay, right? So all of this, and so what is ultimately quantum learning here is that your quantum learning is that means you are actually making your quantum kernels learned so that it can generate a distribution which can help your measurement. So what is the measurement in the if you try to define a classification problem? A classification problem may be converted to a quantum classifier where we define that if my probability of this particular if this particular vector, okay, for this particular class, class is high, then this vector represents this class, and for another vector, okay, it can be another class which probability is high. So this defines another class. So all these classes can be your outcome basis. So you can define these class levels as your outcome basis, and you can train the quantum circuit in such a quantum kernels in such a way that when you give a particular data, when you give a particular vector, okay, the vector will map to a particular measurement basis, and that will define the class level of that particular vector. And that's the way you have to train the quantum circuits. Okay, so I'm almost end of this thing. So this is the way you can actually do the things, and this is the quantum circuit, quantum neural network, and all these things, okay? And you can go ahead in doing the things, okay? And all the things you can do, okay? So this is one of the work which we did. It's not a quantum machine learning, but this is a very good problem solution of the optimization problem of quantum ant. I'm not getting into the details of this, but this fetched us the Quantum IBM Researchers Access Award in 2021, the first research group in India to get this award, and we solved the problem of how we can annihilate and we can assimilate this this quantum ant pheromone, right? And we define a quantum mechanical problem out of that. Okay, this is what is going to be. Okay, when I did my PhD, I thought the quantum computer will be something which is just sitting in my table, right? But that will not be there. Now quantum will be on the cloud, and we have a lot of things to do. Distributed quantum cloud, distributed quantum systems, and we have the middleware, and we try to get the classical software, the software to the endpoint of quantum QPUs. By implementing this type of systems, which are fine. And this is what IBM has defined. Okay, IBM platform. Okay. But I'm not getting a lot of business problems are there. Okay, if a lot of things that the people are trying, and we are very hopeful. There's some very important problems which are very Okay, and there are certain challenges, as I said, that noise, how to handle larger circuits, how to get larger quantum qubits, right? Classical quantum integration, and the quantumness of an algorithm, how to make a verification or how to make a suitable analysis to make the quantumness of an algorithm, okay? Right, these are all, and we are trying to do not many things in our department. I'm skipping this, okay? Okay, I'll stop here. And this is also we are doing with industry. You know, cell technology is one of the very strong industry in India, and we are doing some work with the good, some problems we are working with the industry also and trying to solve some business problems in this domain, okay? These are my students, right? We have fantastic research groups. Some are already graduated and will be graduating, but I'm already recruiting students that will each year, at least 1 2 students in quantum computing group, right? And we work on these different areas like quantum CAD algorithms, machine learning, and cryptography, right? And thank you all for this, right? And these are the things I've already discussed, right? And thank you. These are the good references in quantum machine learning. I have that means if interest is there, I can push this PPT to all of you, okay? Right, and thank you all. Thank you all for listening to me, and I end up here.
Thank you so much, Professor Amlan. Am I audible? I had a small network issue.
Yeah, you're audible perfectly.
Okay.
Audible
Okay.
perfectly, yeah.
So thank you very much. Last minute, I had to drop off from the main network. It's okay. Like I was listening to you. Thank you for enlightening session and guiding us through the fascinating world of quantum computing once again. So your insights have been truly broadened the horizons and inspired, I think, to explore further in this revolutionary field, you know, like you have been talking what it was in 2012 and where we are standing in 2012 and 24. And I remember that this quantum computing was really physics domain, in physics domain for a long time as a theory, and how this advancement in computing has really helped us in moving to the next one. And I'm sure that let us embrace the challenge and opportunity and the problems of the possibilities of tomorrow also. Thank you once again, and it's open to questions. Any questions, please feel free to ask or write it in the chat box. I think we are right on time. We have another 2 minutes more.
Thank you, Doctor. Thank you so much.
Thank
Dr.
you. Thank you, sir.
Thank you for great presentation and moderation. Thank you. So now
Thank you all.
move to our next session. I think we still waiting.
Yeah, I'm just wondering if Professor Roger Jerdak is here. No, I'm going so. Islam, so maybe we just have to wait for him. Yeah.
Yes.
You want to pause the
record?
record?
Reminder now, in order to ensure that.
Yeah. We need to follow the schedule, otherwise it's a bit more confusing.
Exactly.
Yeah.
Exactly.
So maybe you'll just pause the recording. It's still being recorded.
Yes, he's there. Professor Raj, how are you?
Oh, hello.
Hello, how are you?
Hello, Professor Raj. Yeah. And so I am the moderator. Okay, so I'll just quickly introduce the okay, Professor Roger Jerdak is the chair of applied data science with the Queensland University of Technology. So we are neighbors. Hello. He did his master's and PhD in the UC Irvine. Yeah, it's in California. Yeah. Over the years, he has achieved a lot. For example, he has published almost 300 peer-reviewed papers and wrote several books, authorized books on Internet of Things, blockchain. This will be part of his topic today. At the same time, he's also the editor of IEEE transactions on network and service management and ad hoc networks. So with that in mind, let's welcome Professor Jedek talk about the distributed systems. The title is Trust in Distributed System. Welcome.
Thank you, David. And thanks to the IEEE Computer Society for organizing this event. All right. I think, okay, I need to share my screen.
Yeah.
Right. Okay. It's afternoon here in Brisbane, so good afternoon and good morning or good evening, depending on where you're joining from. And thank you for the introduction. So in my talk today, I'm going to cover trust in distributed systems. And specifically, I will talk about two different kinds of distributed systems. One is cyber-physical systems, and the other one is the web. And it's important at the beginning of the talk to also acknowledge our collaborators over the years for the work that I'll talk about today. I won't mention them all by name, but thanks to all of them for this work that culminated in the outcomes that we had from the work. So let's start with cyber-physical systems and what we mean when we talk about cyber-physical systems. So really, we're talking about systems that couple the physical and digital worlds. So they capture data from the physical world with sensors, and they can actuate also, so change the state of the physical world from the digital world. And we deal with networks that connect them, which is currently referred to as an Internet of Things. Sometimes cyber-physical systems and Internet of Things are used interchangeably. So essentially, it's a very powerful technology that allows us to create this interface between the very large digital space and our physical world. And over the past 10 years or so, we've seen a steady growth in the number of Internet of Things devices that allow us to bridge this cyber-physical space. So there's been continuous increase in the number of these devices, with roughly 10% projected increase from 2018 to 2025. And we have currently tens of billions of these devices in the world. So we have, many times more of these devices than we do people actually in the world. And because of this scale, we also have a lot of data that's being generated by these devices. So whether it's a modern car that has many sensors, or jet engines, or more emerging renewable technology, there's a lot of data being generated by many types of these devices that really creates a data tsunami. And so definitely scale is an issue when we think about managing these devices and ensuring that they are serving their intended purpose. And the current architecture of centralized management of these systems, where you have brokers that centrally receive the data and make decisions, does not scale when you're talking about that large number of devices. Because currently, most devices are identified, authenticated, and connected through cloud servers. And then even when we have two IoT devices that physically sit next to each other, they may have to communicate through the internet in order to interact. And that's not efficient and not scalable. So that's one challenge from these systems and networks. Security is another major challenge. And we've seen over the years a lot of cyber-physical attacks happening. This is where an attack crosses the interface between the cyber and physical domains. So in 2010, there was a Stuxnet worm in Iran that targeted its nuclear facilities, and that was spread through a USB stick, actually, that was inserted into a computer in that facility, which actually led to physical damage to that facility. If we fast forward to 2016, many of us may have heard of the Mirai botnet, which is a distributed denial of service attack that affected millions of devices in 2016 and brought many websites down. Again, that was a cybersecurity attack that affected many services that we rely on in the physical world as well. In 2021, there was a Colonial Pipeline attack, which was a ransomware attack that essentially froze the supply of oil in the US for many days, for many parts of the US. And then we have the Industroyer attack in Ukraine in 2022, where cyber attacks on the electricity network caused outages. So again, we see a cyber attack causing physical damage. And all of that has led our government in Australia to pass new legislation in 2022 defining critical infrastructure, which actually is very broad and defines things from banks, supply chains, the power sector, the water sector, all as critical supply chain, critical infrastructure, where the providers of these services have to meet certain security requirements in order to be compliant with the legislation. So this is a major challenge as well, cyber physical security. We also have the challenge in the current model of our internet, where we have isolated data silos. So we have many big players that hold a lot of our data. And once that data is with them, we have limited control over our data and how it is used. And we typically have to trust the cloud and application providers to use our data for the intended purpose. And with Internet of Things, what we see is there are many devices that are collecting data about us in the background automatically without us asking them to do that through a specific action. And because of that, there's much more data that's reaching these siloed providers about us. And that will only highlight the privacy problem even further. So in our research, we asked, is there another way forward? And the answer to that question was blockchain. So we looked at blockchain not as an underpinning technology for cryptocurrency, but as a solution to deal with some of these challenges in cyber physical systems. And in case you haven't been exposed to blockchain before, we'll cover just the basics here about blockchain. So blockchain is a technology that builds on some well-known computer science constructs, including linked lists, where we can have pointers from data objects to each other. Also, it uses asymmetric cryptography, so to use private and public keys in order to secure the information. Then blockchain uses hash functions, which are essentially a way to ensure data integrity, but also to do that by compressing the data. So any data can be compressed with a hash function in order to have a fixed size signature that is unique to that data. And then blockchain uses a peer-to-peer network. So essentially, it uses a large number of computers to maintain a common distributed database, which ensures that no one of these computers can change the information without the others agreeing through a consensus process. And then it involves incentives as well. So for these computers to participate in the maintenance of a blockchain network, they need incentives. And this needs to be built into any blockchain system to incentivize the commitment of resources by the peer-to-peer network participants. So with all these building blocks, what we get is blockchain as distributed ledgers. And what that means is we're aiming to replace a centralized database, which you see on the left, which might have validation rules to make sure that the data entered by many clients into the database is valid, we move from that model to a distributed database where we have many validators that enforce the validation rules. And because there are many validators, typically from many different companies or participants, they keep each other honest. And the purpose of this also is that by not having one single database with one owner, we are also ensuring that there's more sharing of power, and we're avoiding centralization of trust at that database owner. And because of that, blockchain is called a distributed ledger. Now, the validators agree on the current state of the blockchain through a process called consensus. And there are different algorithms for consensus, including the most famous one, which is proof of work, but also others like proof of stake. And there are many others that have been proposed. So then you may ask, is blockchain indeed the answer for cyber physical systems, as we're positing here? And there's a very famous flowchart by Wust and Gervais from their paper, Do You Need a Blockchain?, which takes you through different steps on the situations where you may need a blockchain. So if we go through that, situations where you need to store state, there are multiple writers. So when we're talking about multi-stakeholder scenarios, where we don't have an always online trusted third party. So we don't want to put our trust in a third party to manage everything for us. And in that case, you need a blockchain. If you follow this top flow here and the first three questions. Now, after that, the decision is whether you need a permissionless or permission blockchain, which depends on whether you want to allow for unknown contributors or unknown writers to the blockchain or not. So in our case, we explored this the fitness of blockchain for cyber physical systems, and we wrote a book called Blockchain for Cyber Physical Systems in partnership with Ali Dori and Salil Kanir. And in this book, we looked at the optimizations of blockchain for cyber physical systems and the things you may need to adapt in blockchain for it to work in these contexts. And we also looked at different applications of blockchain in cyber physical systems. And in the first part of the talk today, I'll just cover some of these topics. So one big thing we looked at initially was blockchain scalability. And the reason we looked at that is blockchain essentially provides decentralization and provides it in a secure and immutable way. But it also, the Bitcoin blockchain, which is the first blockchain based on proof of work, trades off scalability for providing that security and decentralization. And the reason it trades off scalability is that all the participants will receive all the updates, all those participants in the peer-to-peer network, and they all can verify everything. And because of that, for a node with a network with n nodes, you have a lot of connections in that. So then you have a low throughput or low rate of transactions. So for Bitcoin, you have 7 transactions compared to 24,000 transactions per second with Visa payment systems. So this is a limitation of the original blockchain. So what we did in our work is we proposed a version of blockchain called lightweight scalable blockchain that is more suited to the Internet of Things and cyber physical scenarios. And the reason we claim this as lightweight and scalable is we make a very important observation about the Bitcoin blockchain. So one key aspect in it is it's required to prevent double spending. That's where somebody might spend their cryptocurrency in one place and then try to spend it somewhere else to trick the system, essentially. But because in Internet of Things and cyber physical systems, that exchange of value, which means that the sequencing is less critical, you're recording data from sensors, essentially, you can relax some of the assumptions and and make scalability more favorable. for IoT. So in this approach called LSB, we proposed a consensus that's based on time. So this is where you have devices that pick a random time to add a block to the blockchain, and then they check on each other that their waiting time follows a random distribution. So this approach is much more lightweight and much more scalable than the proof of work approach, for instance. We also included a mechanism called distributed trust, where the devices within a blockchain, the validators only validate a certain proportion of each other's transactions. And this is based on how much they trust them based on previous interactions. And we also introduced distributed throughput management, which adapts the network structure to the transaction volume that we're seeing. So after we looked at lightweight scalable blockchain, we then introduced another kind of validator selection algorithm to make blockchain scalable and lightweight. And this was called tree chain. And in tree chain, the main innovation we did was saying rather than having one chain, which is the conventional blockchain approach, why not have parallel chains, parallel ledgers, where each ledger is maintained by a particular validator. And this way, we don't have to, the nodes don't have to compete to add a node to the longest chain, but actually they can parallelize some of the block creation and make things much faster. And the structure of tree chain is that there's a genesis transaction, then there are multiple parallel chains that are maintained by different validators, and also we have some adaptation. So these can evolve over time, the number of validators and the number of branches as well. So tree chain, being a validator selection algorithm, it relies on patterns that are extracted from hash functions. So basically, we have a random selection of which validator will handle which transactions, but that randomization of selection is something all the validators can determine independently and deterministically. And they do that through the hash function that we introduced earlier. So very simply put, a hash function is takes a message of arbitrary length, and then it's put through a hash function and creates a fixed hash value. And some of the unique features of hash functions is that they're random and that they're unpredictable. And they also have a high degree of collision resistance, meaning you cannot, two messages will generate different hashes, but you cannot, from the hash value, determine what the message was. And the advantage of using hash functions is that they're implemented in all blockchains. So we don't pay an extra computational cost for using that. So with the tree chain, we created a structure where we assign each validator the consensus code range. So this is the range of consensus codes that each validator is responsible for. So we divide up that range among the validators. And we also use something called a weight dictionary, which basically for every possible value in the hash, it assigns a certain weight. And then we have a key weight metric, which is a cumulative weight of each public key hash, which is determined through this dictionary. So in this way, we can take the hash of the public key, as in this table, and then we can determine the key weight metric in order to prioritize or map that transaction to that validator with ID 12, for instance. So we do that for all the validators and all the transactions, but these things can be determined independently by each validator. There's a lot more detail in the paper, but in this talk, I'm staying more high level to kind of give you an overview of the work we've been doing in this general area. Now, the next optimization area we looked at was blockchain storage. And there's a big challenge in blockchain in that it's an immutable database that's stored by many computers. Because it's immutable, whatever you put there stays there forever. And we see for some of the popular blockchains that there's been very high growth in the total block the size of the blockchain. And remember, that is stored by a large number of computers all over the world to maintain the blockchain. So the huge storage requirements are a challenge for blockchains, especially in an IoT context. And another challenge is remote storage attacks in blockchain. So it may surprise you to know that nodes participating in the blockchain currently, there's no way to prove that they're actually storing everything on the blockchain. This reduction, this threat to the blockchain may compromise data availability and integrity and some of the decentralization advantages that it has. So some of the attacks that are possible for blockchain in terms of storage include the Sybil attack, where an adversary may create numerous fake identities, or an outsourcing attack where an adversary may pretend to store data locally, but then it might rely on another storage node. And the adversary may do that to save on the storage space and cost of maintaining the data locally. And then there's a generation attack where an adversary may pretend to store data locally by generating data that's similar to the real data. So to tackle this problem, we proposed a practical proof of storage algorithm that basically is the first suitable proof of storage algorithm for blockchain. It has a low decoding latency, and it addresses those attacks that we talked about before. And most importantly, it's also decentralized, so it doesn't require any centralized third party. And we do discuss the details of that in the paper below, and also a non-interactive version of this PPOS. But what I wanted to share here is sort of the flow of that. So basically, a device encodes a block. The block needs to be a unique replica of the blockchain data that's available. Basically, you can any validator generates its unique replica that's cryptographically sealed with its key. So that prevents some of those attacks of outsourcing, because you can verify whether that replica was maintained by that particular validator. Then it uses random selection of verifiers and provers using the hash of the new block, similar to our tree train approach. This removes the data owner's role, which is common in some of the previous proof of storage approaches that were not for the blockchain space. And then we design it in a way that actually encoding takes a long time, but decoding takes shorter time. And we set a threshold time for proof response. And this is to detect outsourcing or generation attacks, because then if there's a malicious node that is outsourcing the storage, it's going to take it a long time to retrieve that information from another entity. And during that time, it would have passed the threshold, so it would get detected by our protocol. So this is in terms of proof of storage. It's important to have proof of storage because before trying to reduce the blockchain storage burden, you need to first understand who is storing what and be able to verify that. Then we moved into a way to reduce the number of replicas for blockchain. Remember, we mentioned that blockchain stores everything on all the validators. So in this research, we looked at whether we can reduce the level of replication in blockchain while maintaining the properties, the security properties of availability and integrity. So to do that, what we did is we recognized that there are different classes of devices that may generate and store data, and that may participate in the blockchain maintenance as well. So you can have any number of classes, and potentially the lower classes are IoT devices, and at the lowest storage class, whereas the highest one may be the cloud. And typically, the node availability increases as we go to the higher classes, but the number of nodes, the scale, increases as we go down the number of classes. So this distributed caching works similarly to how caching works on your computer, where you store the frequently accessed data in a special memory called the cache. Now, in this approach of multi-level distributed caching, what we do is rather than storing everything on a local memory, we use each node looks at the frequent accesses to the data that it's storing, and then it removes copies of data that's not infrequently accessed. Now, if there's a request for that infrequently accessed data, then that can go to the next storage class, which is more likely to have that data because it has a longer threshold time for removing it. And this example here just demonstrates what I was talking about. At the lowest level of the figure to your left, the storage class 0. So as time passes by, some data is not accessed, so this is removed. But then there's an access request for new data, which is 0010, which is not available here, but then that's retrieved from the next higher layer. And after some time, that is removed as well. You'll notice that in the highest storage class, everything's available all the time because that's a cloud device. And there, that's always the backup. If you don't find it in the lower levels, you can go to the cloud storage. And so we did a lot of analysis on that and found that even with different access patterns, whether it's uniform access patterns to content or exponentially decaying access, which is more characteristic of the attention economy, we save a lot of storage over the conventional blockchain simply because we remove copies that are less frequently accessed from the lower storage classes in this multi-level distributed caching. So that was a way to optimize blockchain storage by reducing the number of replicas. Another approach we took relates to redacting things from the blockchain. And this was relevant for regulations like the GDPR, which is in Europe, which is colloquially known as the right to be forgotten, which says that if you have data relating to you as an entity, you can ask for it to be removed from whoever's hosting that data. And for blockchain, this is a problem because with blockchain, remember, when you add things, they cannot be removed. So we ask the question whether you can remove things from the blockchain without breaking the blockchain consistency, which is that chain of links that verifies that blockchain is consistent. So we published a paper called MOFBC, a memory optimized and flexible blockchain for large-scale networks. We also had an article at The Conversation on how to protect the right to be forgotten in the age of blockchain. And the way we approach this problem is essentially we shifted from storing data on the blockchain to storing the hash of the data and using the Merkle-Tree structure to be able to verify what is on the blockchain. More recently, in 2024, we had a newer version of blockchain redaction, which was more decentralized and also preserves the privacy, which is included in that reference there, but I won't go into that in detail just because of time constraints. So that was about some of the blockchain optimizations that we did. But after we did that, we also looked at the applicability of blockchain in many cyber physical systems applications. We looked at supply chains where blockchain can support provenance and also how we can trust the data in supply chains and how we can ensure the confidentiality of information of the supply chain participants while being able to verify their claims when they put their supply chain data on blockchain. We looked at smart vehicles, and particularly in terms of insurance and autonomous vehicles, where we looked at who's to blame when there's no driver in the vehicle, and how to use blockchain as a distributed framework in order to verify exactly what has happened in terms of evidence, and also then who's liable. We looked at blockchain for energy trading, where we wanted to have secure and private energy trading among different entities. And we also looked at that not just for homes and smart meters, but also with electric vehicles, and how electric vehicles can be enabled to become mobile energy transporters given their large batteries. Other applications we looked at is communication resource sharing in 6G, cyber threat intelligence sharing, and manufacturing and digital twins, and all as applications of blockchain. I'll have a reference list at the end of the presentation in case you want to check these papers out. So that was the first half of my talk, which covers our optimizations for blockchain in cyber physical systems and some of the applications that we have used for applying blockchain. So next, before we go next, just to conclude, there's still a lot of work to be done there, but blockchain is a really good fit for cyber physical systems and Internet of Things. And there's many open research opportunities around security, distributed systems, networks, software engineering, databases, and many more. So the second part of my talk is shifting gears a bit. If you remember at the beginning, we said we'll cover two kinds of distributed systems. The first one was cyber physical systems. Now we'll talk about the second one, which is the web scale deduplication. So we're talking about the web as our distributed system. So one problem we found in this particular research, and I should acknowledge Kevin Sarich because this work is relating to his PhD. So one problem we found was there's so many copies on the internet of the same kind of data. So for instance, in Australia, we file out our tax returns every year. And usually somebody might take a tax form, create a copy. That copy is then for downloading the tax form. Then they might email it to other people to fill in some of the details. Then there are many copies. Then as the same form is backed up. So you can see here for the same generic data, we have a lot of copies, and that adds to the storage burden for people on their computers. And it's also a problem in the sense that there's a lot of data production happening, and it's growing exponentially in the last several years. And the cost per gigabyte of storage is actually flatlining because of some physical limits on how much can be stored physically in the memory. So what that means is the cost to store all the data is also increasing very quickly. And it's also what exacerbates the problem is that encryption is more costly. So that means that hacks can become more painful. And there have been many hacks. In Australia, there have been several data breaches recently with a large-scale insurance company that compromise a lot of citizens' private information. Also, it's hard for people to back up their information because they're generating so much data. So that's where ransomware attacks are more painful, because then when ransomware happens and your data is locked, you lose more of that data. And there's been a significant increase in ransomware attacks over the last few years. So also the large data volumes tend to make it harder for people to secure their data. So it leads to poor data security practices. Now, deduplication is what this research focuses on. And in a nutshell, deduplication is this. So we have typically big files stored on computers, which might be the operating system files, large images, videos, anything. And this is a typically a group of ones and zeros stored on your computer. Now, what deduplication does is it replaces that big file with a pointer to the source. And we'll see later how that can be done. But essentially, we're shrinking the volume of data that's needed to be stored, because we can, rather than storing the actual data, we store a pointer to where the data is. So with this approach, we have we require less computing to encrypt, and there's less bandwidth to transmit because the pointer is much smaller, and there's less storage to back up for the same reason. But in order to be able to do that, the source of where the actual file is must be trustworthy. So that's the key caveat there. So in this work, we look at large-scale deduplication and what we call universal deduplication. And for that, we need a big common pool of data to draw on. So we asked ourselves, where could we find such a thing? And the answer is the internet. So we used our hypothesis is we can use the web. And this is an evolution of the structure of the web over the past 20 years or so. And you see there's a lot of URLs and sites and links that are stable, although some come and go over time. So this the web is essentially becomes our very giant database and source of files. So what the aim is, the web becomes our backup for the files, knowing with high probability that the files we need are on the web. We can have a recipe to recover them from the web. So that is the main hypothesis of this work. And the data set we used for this work is called the Common Crawl. This involves petabytes of data, and essentially it's a open source project, a public good in that they build and maintain an open repository of web crawl data that can be accessed and analyzed. So it's been going on for many years. We analyzed it from 2014 until today, using 3 high-performance computing systems of different organizations, and we processed trillions of URLs and captured hundreds of billions of URLs. So essentially, this is all the URLs on the internet, but not just today, going back many years with snapshots every month. So it's a gold mine of data that is open for anybody to use, but we used it for this project in order to explore how the web can be a backup for our files to support deduplication. And in using the high-performance compute systems, we had some tension with some of the people managing these systems because of the sheer volume of data and processing and bandwidth that is required for these. And this is just a message from our IT support to that end. So first, we looked at what would it take for us to realize such a vision where we have universal deduplication using the web. And keywords there are security and efficiency, so that we can use cloud storage, but we can use it securely and efficiently using universal deduplication as a key layer there. So we ended up designing this architecture. So on the left, there's a sort of conceptual approach. So here you have multiple users, each with their own, with the same copy of a file X. And in the middle, you have the universal deduplication service, which is what we're building. And at the top, you have the cloud service provider that essentially just stores recipes. So instead of storing files as they do today, they just store recipes of how to retrieve files. In this case, if user C removes file X, then the recipe that's stored at the cloud storage provider knows how to get file X from at least one web server so that C can recover its file. Now, in a more detailed depiction of that architecture on the right, we have basically the universal deduplication service, which involves many components that we built and links up with the internet. That's on the server side. And then on the user side, we have file monitoring to know which files, the types of files we have, processing of those files. We use the universal deduplication service to be able to have an availability check and trustworthy availability check of the data. And then we also have a key component we developed, which is the recipe generation. The other components can be adopted from other existing systems. So we focus on the yellow highlighted components in our research. So first, what we found when we analyzed the common crawl data is that there's a large quantity of vulnerable domains. There's a lot of abandoned domains, and we've redacted some of them here for privacy. And there's also a lot of web developer typos. Basically, the y-axis here is the domain reach. So this is the number of referring domains to each of these domains. And we find, for instance, for this one, we have about 20,000 domains that refer to this domain that has vulnerability. So that's something that we found as we analyzed this very large data set. So there's really a necessity to integrate, necessity for integrity checks of the URLs, so that if we're relying on them to retrieve files, we know that they're going to be trustworthy. We also found that when there are, in certain scenarios, the cost of universal deduplication is significantly lower per user on a cloud service provider than the current approach. And it's also important to note that most current cloud storage provider storage these days is, although it's encrypted to reach the cloud service provider, they typically have access to it to see it in plain text, which is also a major privacy or confidentiality risk. So in this paper, as part of this work, we looked at how we can predict the availability of files on the web. So what we did there is we analyzed a very large number of header requests. This is only metadata, so we didn't download the files. We looked at the metadata of the files across all file types, and it's what we think is the biggest header data set yet. But we also focused on some of the larger files that may sit on a person's computer, which may be audio, video, executables, and archives. And we did find an interesting pattern in the distribution of these as a power law. So this is related to the age of the largest files on the web, and the different colors here indicate different types of files. What we did is we fit a power law to the age of the files that we observed, and power law was a really good fit, a really good estimator of the age of files, because we tend to have many files that persist for a very long time on the internet, whereas we have a large number of files that are transient and may disappear as well. So in this predictable availability framework, we have the internet, which is on the top left of the figure. We have a universal deduplication service that essentially does does availability crawl for a file F. Now we use Bloom filters to determine whether the file we're looking for is available in that crawl, and then the files that are large that are widely available can be, rather than storing them locally, we create a recipe which is encrypted end-to-end and sent to the storage provider. So we only store the recipe at the storage provider, and whenever we need the file, we can retrieve our encrypted recipe and then retrieve that file from the internet rather than storing it locally. And that saves storage space for all these users. So this is the detailed process of how we designed the predictable availability framework. I won't go through all the details, but essentially what you need to know is that this approach estimates the lateral and longitudinal availability of a file. So what we mean by longitudinal is the file available over time, that age estimate. And for lateral, what we mean is, are there multiple copies of this file? And if so, how many? And based on that information, we predict the lifespan or the likelihood that we'll find at least one copy of that file online in the future. And based on that lifespan, we decide whether we can rely on the online copies to retrieve the file based on our risk appetite for that retrieval. So we also designed an extensible mathematical model in order to assess these issues. So in the first equation there, LP is the predicted total lifespan, and we fitted a power law as we discussed before. So we use the current observed lifespan, so how long the file has been alive so far, to predict the total lifespan by using this exponent that we fit from empirical data. And in the second equation, we have the specified per source lifespan probability. So that's for each source that has this file, we can have a probability that the predicted total lifespan is greater than the desired lifespan, given that we know the current lifespan. So using those two equations, we can then determine the probabilities and figure out if we want to rely on these existing copies of the file. But also during our analysis, we found some interesting observations in that for most files, there's this transient volatility state. So in the first 5 months that files appear online, basically the count of the file, the number of copies is lower, and then somehow they reach a state where they're less transient and there's sort of more availability of these files. You can see here this step change of increase in the file counts, which is quite interesting. So we did an evaluation where we did what if analysis. So we went back in time to the oldest trace, one of the older traces we had from the common crawl. And then we use this formula to predict ages of files into the future. And then we quantified the confidence interval of our prediction versus the real. So we predicted a year after we had some observations. And then we looked at the confidence intervals. And we found that most of the average URL lifespans fell within our 80% confidence prediction. So what we found from this availability analysis is that there's a pool of about 2,500 terabytes of highly available popular files is available to use as a potential backup and restore source for our files. And so we built the university duplication service and the trustworthy data availability check. And currently, we're finalizing the recipe generation that will complete the picture for this university duplication. But along that journey, we actually discovered something really interesting, which is called hijackable hyperlinks, which I'll talk to you next. And this will be the last piece that I'll talk about today. This was published at the web conference in 2024. Now, the idea is hyperlink programming can involve errors. So if you're familiar with typo squatting is when, as a user, you might make a mistake when entering a URL. So you might add an extra letter to a URL and go to a wrong place where attackers might have a fake website that gets your information. Hyperlink programmers can also make mistakes. Many people can use templates for programming websites, or they might add a character or remove a character. But this is much more significant than user errors, because once an error is in the website, then that will always be there until it's discovered. And that can then be exploited by attackers at scale. So as an example, this is what the HTML entry is for a particular web page, where you have a reference to a URL. In this case, the programmer typed Gmail with an extra L. But this is what the user sees on the right. So the user sees the correct address, but it actually takes them to this erroneous link. So in our work, we call this a hijackable hyperlink, because this domain, if Gmail with 2Ls.com was never registered, then somebody can hijack it because it's a phantom domain if it's never registered, and buy that domain and actually have a fake Gmail in that location. So if they do that, then let's say they create some realistic interface and ask somebody for their Gmail password, and all of a sudden the Gmail account is compromised. So this is potentially a big risk that we found through our analysis of the common crawl. And in order to find these domains, we defined this process that essentially filtered based on multiple data sources the domains from a common data crawl to arrive at the likely phantom domains. So going through that, we started with about 43 million .com domains. We only focused on the .com domains for this analysis. And after doing all that filtering, we found that there's about 500,000 domains that there are links in existing web pages to these domains, but these domains have never been registered. So these are phantom domains, and the links pointing to them are hijackable hyperlinks. So what we found is that the highest proportion of these was at WordPress and Blogspot. So these are blogger sites where anybody can contribute content. That increased the likelihood of hijackable hyperlinks. We also found that there was greater programming errors at these, because typically these are not professional programmers that add that content. They might use design templates or code-generated links. But we also surprisingly found major websites, including governments, that have these hijackable hyperlinks. And we actually found some of the biggest companies in the world include those on their website, probably unknowingly, which is quite a big risk. There are financial companies and news sources and tech companies that have these hijackable hyperlinks. Obviously, we're not reporting that here for privacy. And there's also major universities that have that as well. So what we did then is we registered dozens of these phantom domains. So we bought the domains, and then we observed the traffic, the incoming traffic to those domains for a week after they were registered. But we also bought a control domain, which is not a phantom domain. So there were no links, no hijackable hyperlinks on the web to that domain. And what we found is that there was a significantly higher traffic to the phantom domains than to the control domain over that week, which basically 88% of them exceed the traffic of the control domain, and one of them actually had 10 times the traffic over the control domain in that first week. So after doing those analysis in the paper, we propose different countermeasures that both for internal and external countermeasures for organizations and approaches to mitigate and fix the problem when it's there. But essentially, the theme to all our proposed approaches is raised awareness of this problem, both among users and within organizations. So just to summarize on these hijackable hyperlinks, we found them on websites of many of the world's biggest companies across all major industries, on many government websites, because many of the government websites use popular website design templates. And then we also even found them in privacy legislation plugins, again, via programming errors. So here are some references, particularly for the first part of my talk. And with that, I'll conclude and ask if you have any questions.
Oh, thank you very much. It's a very, very comprehensive work. I mean, you have done a lot of work in the university, and very, very impressive. So So I'll open the floor for questions. We have 5 more minutes. If not, I do have a few questions myself. So anyone does anyone have a question? Okay, so okay, let me go backwards. You know, it's very interesting. The first question is that you know, you talk about hijackable hyperlinks, and you actually did some work. You registered domains and then monitoring the okay. What in your experiment? What is the most effective migration strategy you did to avoid this problem?
Yeah, I mean, this is something. There's no one solution, I would say. We have been exploring several options, including building a plugin for browsers that can detect these. But there are challenges there as well, because if you have a plugin in your browser that tells you whenever you go to a URL, you might be going to a domain, like a phantom domain, then that might become a tool for attackers to identify those phantom domains. So we are exploring a way to do that in a silent way, and we're also talking to some major top-level domain administrators on ways we can do that in partnership with them. There is other than that, there is direct notification to the sources, but there are 500,000 of them, so it's a lot, or maybe more than there are 500,000 phantom domains, but there might be a different number of source domains, and also a recommendation for thorough review of the outgoing hyperlinks from existing domains to make sure that they don't have phantom domains. So it's a long answer, but it's just to say that there's no one solution, but we're still in the process of exploring something practical that can work.
Thank you. That's interesting. We have 3 more minutes, so I have one more question. I have a lot of questions, but the next one, you were talking early about MLDC, right?
Yeah.
So you use that you want to achieve data privacy, and you also want to maintain transparency. That's a contradiction. How do you maintain that? How do you ensure the data privacy where you maintain transparency? That's a question. Thank you.
So MLDC, you mean the multi-level distributed caching?
Yeah. Yes.
So in MLDC, the main purpose was to basically reduce the blockchain storage footprint. But I agree with you that challenge, like the trade-off between transparency and privacy, is always there, because once you have full transparency, you lose privacy potentially. So in that context, we didn't explore that trade-off explicitly for MLDC, but we did explore it in some of our other work, including our blockchain for supply chain work, where we used things like, for instance, we used zero knowledge proofs and Pedersen commitments, where supply chain participants can prove certain attributes about their products without revealing the actual data. And we also had a separate work where we used separate blockchain ledgers, one for maintaining the decentralized identities of participants, and the other one for specific trades on the supply chain. And then we have tokens to basically interact between the two, tokens that are authorized by the decentralized identity owner. So it is a continuous challenge, privacy and transparency, but there are some tools that can help.
Okay. Well, thank you very much. I think I'll email you because a lot of these areas, my students also got involved. You mentioned the zero knowledge method and all of that. Due to the time constraint, I'll email you and I'll get some more information offline. On that note, I would like to thank you very much for your talk.
Thank you. Thanks all.
Okay, back to you. Just wondering, the next presenter is
continue our recording. So now it's time for the SYB session. So it's not technical session, but it's our pleasure to include you in this event and hear from you. So we are happy to host you. So the floor is yours.
Yeah,
Thank you.
sure.
That's good. It's non-technical. Finally, I can understand something now. Please go ahead. Welcome.
Yeah, hey. Hey everyone. So sorry that Shivam had a last minute meeting, so he wasn't able to join. So you have to cope up with me. So yeah. So let me start with sharing my screen. Is my screen visible?
Yeah, perfect.
Yeah. So hey everyone, I'm Vishwarup Rai. So I'm actually the chairperson of Early Career Speaker Programs under IEEE CS, and I am also a senior engineer in ZS. But yeah, so I'm here to actually explain a bit about what IEEE Computer Society SYP is about, and what we do, what's our whole dream is, and what we are actually about, and what we are going to do in our future. So first, let me talk about the vision that means our chairperson Saptashi and even Shivam, who is the advisor and the chairperson of New Initiative Committee, preaches, is that we have a dream to actually empower every student and young professionals across the world in the field of computing. So means the mission is actually of empowerment, but the way we empower is not just through getting volunteers or getting members in, it's through spreading the message of SYP throughout. So means SYP actually tries to get the whole concept of IEEE Computer Society, IEEE other RAS and all the societies, and try to bridges the gap to get that thing in to the students and the young professionals. It could be means young professionals could be early career professionals who are in most of them are just starting their career. It could be even people who are actually restarting their career. So we are someone who actually tries to get to those people in. So now let's talk a bit about yeah, let's talk a bit about our vision, means our vision and the future planning what we have and what is our whole plan of action that we want to do. So the first thing that is we want to do is always lead by examples, and we have great leaders in our IEEE Computer Society. We have great leaders in SYP as well. So all those leaders are actually present us with those case studies. So even let's talk about Shivam a bit. Let's talk about his work in his career as well. So he actually preaches climate sustainability through different architectures, through different projects with his client. Even our programs which we do nowadays is actually carbon neutral programs. So those events we do which actually we try to limit the means actually try to make it more sustainable and more climate friendly. So that's something. Then it's always about when you have a member set, and we have this community of IEEE Community Society SYP. It's always about creating awareness among members. So there are multiple events that are going on. We have AICSSYC, we have Region 8 Congress, which recently is happening right now in Egypt, and also we even have podcasts like IEEE Fireside Fusion, which we have with other senior leaderships from IEEE CS, like we had just with Grace Lewis, who is the who is going to be the interim president, and we even had with Hironori, who is going to be the president in 2025. So yeah, we have those podcasts. We try to create the awareness. We talk about climate sustainability there as well. So there are even pilot programs. We have climate sustainability based programs as well, which we support. We even have a branch named as climate and sustainability in our IEEE CSS5P. So we promote that there as well. Then it's all about adopting and learning from the pilot programs. So we have those programs. We need to adopt those programs into our other programs, other things, other learnings, and all those things is something. So means climate and sustainability and IEEE CSS5P is something we try to talk and get into hand in hand. So that's something which we are planning to do. Now, talking about leading by example, I just gave you a bit overview. So when Shivam and me, I also work in ZS Associates. So when we go to a client, the way people ask with this whole Gen AI and all those big models and LLMs coming in is that means there's a concept that when you prompt, even if you try to give 10 prompts to ChatGPT or the models that's hosted by ChatGPT, you actually get 500 ml of water. You need 500 ml of water to actually cool the servers down, to actually write 10 prompts. So that's the whole case with ChatGPT coming in. So yeah, means this. So it's not always about carbon friendliness, it's also about water friendly models, which we talk about in our with even with our clients, with our programs. So that's something we always talk about. So then what we did is we studied about open source models. So all those open source models actually can be integrated through a serverless architecture. And not going into too much detail, I don't want to give a technical talk, but serverless models are basically, if you are prompting to it, or if you want that model to work, it will work. Until and unless you are not prompting it or you are not using that model, it will keep on switched off. So that's the way you can actually limit your servers, or actually limit the physical servers operating capability, and get that serverless architecture in to actually consume lesser amounts of carbon emissions and lesser amount of energy. So that's something we actually propose, not only to our through our IEEE society programs, but also through to our clients, and also through each and everyone we go to. So yeah, this image is actually an awareness drive which Shivam led, which is on efficiently using generative AI through serverless setup. He actually did it in an SYP event, which he also did it in a Region 8 event as well. So there's SAP who went to the went to so we actually collaborated with different partners as well. We went with the UN Climate Sustainability Board and actually preached the whole thing about SYP's awareness towards climate of sustainability. So that's something we preach about. Now talking about our collaboration. So when you talk about IEEE or IEEE Computer Society, you talk about the technical and conferences, right? So it's always about the conferences, it's always about the technical projects or the journals that IEEE has. That's the normal way that IEEE is being recognized throughout the world. So we have actually proposed some initiatives for students and young professionals to those conferences and to the TNC board. So some initiatives which we actually proposed are we actually propose a student travel grant awareness and a centralized repository for funding. So what that means is that nowadays what happens is normally students are not aware of the conferences. We actually had a chat with I was actually had a fireside fusion chat with Terry Benzel, who is actually the vice chair in for TNC, vice president of TNC. So she actually mentioned this thing as well. So she mentioned that nowadays what happens is that students, whenever they are actually going into conferences, they are not aware means they are not aware what actual conferences is going on. It's normally PhD students or students who are in their actually there as a professor, or people who are as a professor who are actually aware of these conferences going on. So we actually wanted to create proposed a student travel grant awareness and a centralized repository for funding, which will help students to be aware of these programs. Then we wanted to engage industry. So this is something even Grace, who we had a chat as well, she also mentioned that it's very important that industries get into these programs, and we have started doing that. So it's not only academic based programs that the conferences need, it's active industry experience which the students need. So normally when you think about conferences, you think that academia will go and present their papers and come back, but nowadays it's actually industry papers with this whole Gen AI and the concept of research coming in and R&D coming in. It's industry who has collaborating. And to get students to interact with them, we actually mentioned that, hey, why not have postgraduate members and industry people, industry folks, be as a mentor to those students. So that's something that can be done, and that can be done through either technical projects or academic postgraduate members giving projects to the students as well. So that's something we proposed. Then further exploring the industry conference part, we actually wanted the YPs who are there in industry. So normally managers and principals who are there in an industry won't be able to come and give a talk about it, right? So it's majorly the young professionals or the people who are in their early careers in that industry who comes in present papers, which is actually a lot happening. So I myself is a YP, I am an YP, so I also presented a paper in which was present in IEEE SDS, which is a Swiss data science conference, and then IEEE conference. So people are collaborating with Databricks as well. There's potential with AWS summits, Databricks summits, which can be brought in, which can include those YPs into those industry conferences, which we proposed. Then means even a lot of conferences nowadays have started doing industry based papers. So there are research papers, there are industry papers. So the industry papers are short abstracts from industries, are something which is very helpful. Now coming on to, we have actually a program which is TechX. So TechX is an IEEE CS SYP initiative which focuses on local initiatives. So there are a lot of local chairs, local events being hosted, and these events actually have a umbrella of TechX. So TechX actually collaborates not just with students and young professionals, it actually brings young industry professionals, and that too in that region. So talking a bit about my program as well, which is early career speaker program, what I have is, I have means people coming in, not talking too much about technical, having a mix of technical and non-technical into their talks, and giving that support or that mentorship to those people coming into those events, giving that speech about some early career talks, like how to get into research, how to get started with your career, how to get started with entrepreneurship. It could be something like how to make sustainable models, how AI can be made more responsible. So having a mix of we have a mix of industrial speakers, we have a mix of academia speakers. So those speakers are actually presented in a lot of regions, and whenever we have a local event being hosted through TechX, we actually call those speakers in from those regions, so that means we have that whole local flavor to it, so that regional speakers come in, they give a speech, they give a mix of a non-technical plus technical speech, and that's the way we are envisioning of a collaboration with the whole regions. So yeah, that's a bit more about our collaboration with it. So yeah, this is a page I always like to present to everyone. So the way we as an IEEE Computer Society SYP activities portray us is, we act as a bridge among all the other boards, all the other initiatives that IEEE CS has. So, and we act as a bridge with the students, the early career professionals that are there. The early career professionals could be professionals who are starting their journey, could be professionals who are restarting their journey as well. So yeah, so we act as a bridge. We have those programs such as TechX, we have member and geographic activities board, we have different programs, different regional events as well. For technical conference activities, I just showed that we are doing TechX with industry professionals. We are trying to propose some programs inside the conference activities as well. So we have the new initiatives committee. My program falls under the new initiatives committee, but it's a collaboration among IEEE CS S5P. So yeah, S5P acts as a bridge among students and early career professionals and among the other initiatives of the IEEE CS or even IEEE as a whole society. So yeah, that's the way we portray us with yeah. So now coming on to the whole vision. So as a whole, our whole vision was about empowering students and young professionals throughout each and every regions, throughout each and everywhere, through computing and raising awareness. But yeah, means it can't be done without having any programs. So we have a whole lot of programs going on. So we have TechX, we have CSIS, we have AICSSYC, we have different global congresses, we even had Region 8 congresses, which Region 8 Congress is currently going on as well. We have Asia Pacific Micro Summits, we have micro mentoring, all these programs we have. So it's these programs, what they do is create awareness. There are means TechX is a local programs, there are global programs as well. So raising awareness in globally as well as locally, as well as raising awareness into important things such as computing, responsible computing, climate sustainability, all those things are being done through these programs. So going into a bit detail about these programs, yeah. So we means we as a society and even Saptashi as the chair has the vision of dividing this empowerment into different categories. The first category is by engaging with the youth or engaging with the society. So we have programs which are solely based on engaging with the students, engaging with the young professionals, or basically engaging with the youth. So we have CSIS, which is basically computer synopsium, which we recently had. We have AICSSYC. In AICSSYC, we actually bring in the leaders from IEEE CS to have a talk about them. We have micro mentoring, which actually helps students to gain mentors and get their journey in, because mentors are something which are essential for growth for each and every student throughout. So we also have a compute magazine which is being released yearly, and those compute magazines are actually all the programs, all the things, talks, speeches, the experiences of people, young leaders from our society as well, and those are used to actually engage with the students. Then we have programs to actually grow, and growth doesn't only mean growth for students or S5P. It actually means growth for each and every regions, each and every areas, each and every means growth of society, IEEE S5P throughout the regions, throughout globally, and it also means growth of each and every students. So we have TechX, which is a regional event which is being hosted by regional chairs, regional societies. We have Region 8 Congress, which is also a Region 8 event. We have Global Congress, which is a global event which is spread throughout. We have Asia specific micro summits. We also have rooftop socials. So rooftop socials is a new thing which we have a recent event which we have started doing, which is mainly done to actually have that growth in through the other regions as well. Then now bringing into the flavor of the industries as well. So we not only have students who are there in their academics, but we also have early careers, young professionals as well who are present in the industries. So we want that industry experience to come into the programs as well. So TechX, we have started bringing in industry experts. We have early career speaker programs, bringing in speakers from young professionals and all those things, talking about their industry experience, how to get into industry, how they manage their industrial experience with the research. So stuff like that. We have climate and sustainability talks, which Shivam mainly leads and gives to to all the experts. We have industry collaboration regarding climate and sustainability. We have data. We are trying to bring in Databricks summits. We are trying to bring in AWS summits into climate and sustainability talks. So we also have different high impact events which we do, which we bring in industry experts, and micro mentoring also is done by both academic young professionals as well as young professionals from the industry who mentor the students and different people throughout the journey. Now coming on to the important part about diversity and inclusions, all our programs are actually very inclusive and friendly with the whole society. So we take diversity and inclusion into accordance with our programs. We have AICSSYC, which is led by even women. We have AICSSYC, which is spread throughout the regions. We have climate and sustainability talks given throughout the regions. Even our all the events are actually focused on getting the diversity and inclusion in. We have a team inclusive of each and every people. We have a team which is throughout the regions. So yeah, and I'm always happy to show this page to everyone because this is something which we have done recently. In 2024, this is the number of activities and the regions we have actually planned and completed the events on. So means you could see from the map that it's throughout the world. Means we have had events in Australia, we have events in Africa, we have events in South America, North America, we have events in India, in Asia. Means we have spread throughout, and we are planning on increasing those events in 2025 to means you'll see a lot more pop-ups in the recent events. So yeah, that's the whole thing. So ending with means the IEEE Computer Society, we are always available for means we always try to give students, give young professionals, give each and everyone updates on what new initiatives we try to launch, what initiatives we already have, which we are doing in different regions. So yeah, means feel free to contact us. There we have our social media handles which spread out the whole communications part on whichever events we are hosting, which events are hosting in your region, in different regions. So yeah, sign up, be aware, and yeah, spread the awareness to each and everyone. That's the whole thing I want to say. Thank you. Hope I had give you a fruitful talk. Any questions, anything anyone has?
Thank you for sharing this fruitful information and message from all the students, young professional, the computer side. Thank you.
Yeah. Yeah, it's always great to spread awareness because it's our whole society is about spreading awareness and empowering people, right? So yeah.
Very good. Very good. Yeah, thank you.
I should be next, so we can wait till the time.
Yeah, I think we will have about a half an hour break until the next one. Yeah, we need to follow the schedule. Okay, go to get some coffee and vodka, glass of
and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program. The IEEE Computer Society's Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interaction, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
Computing is expansive.
Computing is evolving.
Computing is limitless.
We are the IEEE Computer Society, the professional home for all computing.
We bring together passionate engineers, scientists, academics, and industry to cultivate environments for idea exchange, dialogue, debate, and collaboration.
We set the standard for learning that empowers, with peer-reviewed publications and international conferences, local chapters and meetings, and valued resources.
We support members, we cultivate leaders.
We help computing professionals at every stage of their career.
We are the IEEE Computer Society, your professional home.
Hi, I'm David Allen Greer, the IEEE Computer Society President for 2013. And I'm here to talk about the community of professionals that you join when you become part of the IEEE Computer Society. Usually when we talk about the benefits of joining the society, we talk about those things that you see flashing over my shoulder right now. We talk about the digital library. We talk about standards, periodicals, continuing education materials. Those are all benefits, to be sure, very real benefits. But people will say, I get the digital library at work, so I don't need to be a member. Or I get periodicals in other ways, so I don't need to be a member. I have exactly one standard I ever use. I already own it, so I don't need to be a member. Those arguments have some truth in them, but they miss out the point that you are investing in your professional career by being a member of the Computer Society. You're joining a community of people who, for over 60 years, have worked to advance this wonderful technology that has quite literally changed the world. And when you join them, all you do is need to make one connection a year, and that will be an investment in your career, in how to be a professional, how to see where the community is going, what are the new trends, how you should behave yourself, how you should think as a professional computer scientist, computer engineer, software engineer, or other information professional. These are the benefits. These are the real benefits. You're investing in yourself when you join, because it's through these connections that you really learn to be a professional. Information, you can get that on the internet. Professionalism, you get that from the IEEE Computer Society. We have a web page below that you can click on to renew your membership. Thanks for listening. Take care.
Good morning, good afternoon, good evening, and good night. A greeting adapted from the movie The Truman Show, starring Jim Carrey. And it works here since to each of you there is some relevance in that greeting. And hello, Kuala Lumpur. Sapporo, San Francisco, Wilkes-Barre, Thule, Dublin, Bruges, Cairo, and Mumbai. I'm George Proler, Chair of the Computer Society Distinguished Visitor Program, and it is my honor and privilege to welcome you to this, our second annual IEEE CS EXA DVP event, or as we call it, the 24-hour event. Second annual has a nice sound to it. At the beginning of last year, hosting such an event was just a thought. To extend an earlier project to cover an entire day, 24 hours of presentations, reaching and including our diverse membership. And quite frankly, we weren't sure if we could put it together. But Professor Hassam Fahmy, my predecessor, and Professor Islam Halim, chair of the Awareness and Customer Advocacy Committee, and his team rose to the challenge. And we did it. And it was successful. The first annual. And now, well, Professor Islam and his team have outdone themselves. Look at the agenda for the next 24 hours. Artificial intelligence, AI security and privacy, and research ethics in the area of AI. Quantum computing and the quantum world, smart and high-performance computing, and the list goes on. And we are already working on the planning for the third annual event for next year, taking another step and upping the challenge for Professor Islam and his team, as we are looking to make this a hybrid event with on-ground activities concurrent and shared with the online participants and attendees. This event spans each of IEEE's 10 regions and the world's time zones, hence my adapted greeting, since each of you and the DVs, the presenters, the moderators, you all hail from different and diverse regions, and for some of you, it's 10 a.m., 2 p.m., 8 p.m., and 2 a.m., and all the hours in between. So it is morning, afternoon, evening, and night. Truly an effort of inclusion of our diverse membership base. Today is International Volunteers Day, which is fitting since it has taken, and before this day is through, it will take the efforts of more than 50 Computer Society volunteers coming together from the Geographic Activities Committee, Students and Young Professional Activities Committee, and the Distinguished Visitor Program to bring this event to you. Over the next 24 hours, you will have the opportunity to attend more than 20 technical presentations on topics I've already mentioned, along with informational talks about the Computer Society and its regions, activities, and programs. Each presentation will be introduced by an event moderator who are members of various student chapters, and through participation in this event are gaining experience and opportunity. And then there is the audience. That's you. Many of you are members and affiliates of the Computer Society who volunteer your efforts to make local programs a reality. And all are here allowing us to bring this event to you. So thank you for your time. And now, before I wear out my welcome, I'd like to pass the baton to Professor Irinori Washizaki, the President-elect of the Computer Society. Thank you.
Computing is expansive.
Computing is evolving.
Computing is limitless.
We are the IEEE Computer Society, the professional home for all computing.
We bring together passionate engineers, scientists, academics, and industry to cultivate environments for idea exchange, dialogue, debate, and collaboration.
We set the standard for learning that empowers, with peer-reviewed publications and international conferences, local chapters and meetings, and valued resources.
We support members, we cultivate leaders.
We help computing professionals at every stage of their career.
We are the IEEE Computer Society, your professional home.
The IEEE Computer Society's Distinguished Visitors Program delivers tools for individuals at all stages of their professional careers through visits to chapters, offering opportunities for individual interaction, and to the membership through webinars by respected professionals. We have distinguished visitors who cover machine learning, cybersecurity, robotics, big data, cloud computing, blockchain, and cryptography, among others. Chapters can request a distinguished visitor on computer.org/distinguished-visitors. The Computer Society pays intercity travel, while chapters are responsible for all costs with regard to the hosting of the distinguished visitor, such as lodging, transportation, and food and incidentals in the city of the presentation. The Distinguished Visitors Program is able to pay up to $1,000 for a visit to a chapter, but by working with other nearby chapters to develop a tour, that amount can be increased. So when your chapter is planning its next event, think of the Distinguished Visitors Program.
When I joined the IEEE Computer Society, I was able to lead efforts to make our communities more diverse and inclusive.
When I joined the IEEE Computer Society as an undergraduate in the early 1980s, it greatly expanded my research network and increased my access to the top conferences and journals in my community.
Joining the IEEE Computer Society helped me keep up with the latest innovation and technology trends so that I could excel in my day-to-day job.
Join the IEEE Computer Society today.
Computing is expansive.
Computing is evolving.
Computing is limitless.
We are the IEEE Computer Society, the professional home for all computing.
We bring together passionate engineers, scientists, academics, and industry to cultivate environments for idea exchange, dialogue, debate, and collaboration.
We set the standard for learning that empowers, with peer-reviewed publications and international conferences, local chapters and meetings, and valued resources.
We support members, we cultivate leaders.
We help computing professionals at every stage of their career.
We are the IEEE Computer Society, your professional home.
Well, I am Professor Hossam Fahmy, Professor of Computer Engineering, Faculty of Engineering and Shams University, Cairo, Egypt. I am the immediate past chair of the IEEE Distinguished Visitors Program. Good morning, or good afternoon, or good evening. It is 3 a.m. Cairo time. Welcome to this year's IEEE Global event. It is both an honor and a privilege to participate in the opening ceremony as we embark on this remarkable journey of innovation and collaboration. We gather not just to celebrate the advancement in technology, but to recognize the collective spirit of curiosity, ingenuity, and perseverance that unite us as a global community. IEEE has always been at the forefront of shaping the technology landscape, and this event exemplifies our shared commitment to advancing technology for humanity. Over the next 24 hours, we will witness remarkable talks and engage in thought-provoking discussions. This year's theme, International Volunteers Day, serves as a powerful reminder of our responsibility as innovators and leaders. Whether we are addressing pressing challenges such as sustainability, connectivity, or ethical AI, we stand united in our mission to create a future that benefits all. I want to take a moment to express my gratitude to the organizers, volunteers, and sponsors who have worked tirelessly to make this event possible. Your dedication and passion are the foundation upon which this event stands. To our participants, researchers, industry leaders, and students, you are the heartbeat of this gathering. Your ideas and contributions make this event truly global and impactful. Islam Sarwat, go ahead as usual. George Froller, David Bandurant are usually at the core of success. Hironori Washizaki, all the best in your coming moves. As we open this global event, let us embrace the opportunity to learn, innovate, and inspire one another. Let the exchange of knowledge and ideas begin just after this opening. Thank you, and may this global event be a resounding success.
Hi, I'm David Allen Greer, the IEEE Computer Society President for 2013. And I'm here to talk about the community of professionals that you join when you become part of the IEEE Computer Society. Usually when we talk about the benefits of joining the society, we talk about those things that you see flashing over my shoulder right now. We talk about the digital library. We talk about standards, periodicals, continuing education materials. Those are all benefits, to be sure, very real benefits. But people will say, I get the digital library at work, so I don't need to be a member. Or I get periodicals in other ways, so I don't need to be a member. I have exactly one standard I ever use. I already own it, so I don't need to be a member. Those arguments have some truth in them, but they miss out the point that you are investing in your professional career by being a member of the Computer Society. You're joining a community of people who, for over 60 years, have worked to advance this wonderful technology that has quite literally changed the world. And when you join them, all you do is need to make one connection a year, and that will be an investment in your career, in how to be a professional, how to see where the community is going, what are the new trends, how you should behave yourself, how you should think as a professional computer scientist, computer engineer, software engineer, or other information professional. These are the benefits. These are the real benefits. You are investing in yourself when you join, because it's through these connections that you really learn to be a professional. Information? You can get that on the internet. Professionalism? You get that from the IEEE Computer Society. We have a web page below that you can click on to renew your membership. Thanks for listening. Take care.
Hello, everybody. Welcome back again to continue our event. And it seems that Professor.
Hello, sir. How are you?
Doctor.
Hi, sir.
Hello. So, Dr. Sadi, if you'd like to start the session and introduce Professor Tariq.
Okay, sir. Thank you. My name is Dr. Sadiq Ali Khan. I am the moderator of this session. I am representing as a portfolio officer of IEEE Geographic Activities Committee, Region 10. So, welcome to this second IEEE CS DVP EXA event of 2024. And many congratulations to Professor Islam and IEEE CS for organizing these kind of sessions. So in this session, our honorable DVP speaker is Professor Dr. Tariq Rahim Somro, a senior IEEE member and a rector of Institute of Business Management, Karachi. And he has done his PhD in computer application from China and having extensive 29 years of experience. And he's also representing R10 Southern Area Coordinator of IEEE CS. So today's topic is security and privacy in artificial intelligence. So now I would like to hand over to the mic to the Professor Dr. Tariq Rahim Somro. So I request the audience to note down the question answer, and that we will take a few questions by the end of the session.
Thank you, Professor Sadiq. Thank you, Professor Islam. So today's my topic is AI and digital deception. So I'm audible and you can see my screen also?
Yes.
Thank you. So a disclaimer in the beginning that all the picture used in this presentation are generated using ChatGPT or edited using designer.microsoft.com or deepai.org. So all the images are AI generated images. So I'll talk about actually digital deception using AI tools, what is going on, what are the issues. And then I will technically talk about the countermeasures because we need to understand that a lot of deception is going on. So how to control it, how to mitigate it. So we'll talk about the countermeasures and finally a QA session. So coming to the digital deception, the first example is the deepfake, compromising the biometric authentication. Deepfake threat is very, currently is a big threat. So this technology is compromising a traditional biometric authentication. Normally, people are, the applications are there that you can use your camera and, collect. So cameras, resolution is very high. So easily from the picture, the biometrics data can be captured and can be misused. So this is the technology which is compromising traditional biometric authentication method, like we were using before, facial recognition method or the voice analysis. So deepfake is also, generating the fingerprints or biometrics data. Liveliness detection is also one of the tool we are using today. So some of the applications, they want to make sure that you are still living. So they need your facial expression, looking at up, looking down, looking left, looking right, and they capture videos and make sure that you are the one and you are live. So liveness detection is a biometric system, help differentiate between a live user and AI-generated fake users. Then AI spoofing and cybercrime is one of the problem also. So AI-driven deepfakes are being used in cybercrime to impersonate individual and access-sensitive system. So the videos and other calls are coming, and they are not the real people. They are the deep generated deepfake generated images or videos, and they are trying to fool the people. And normally the ultimate goal is sometimes is to collect the money from the victims. Majority. But again, there are other motives are possible. Again, AI role in cybersecurity, AI enhanced cybersecurity, but it also exploits by attackers for deception, phishing, and fraud. So, okay, AI is helping on one hand cybersecurity, but on the other hand, using AI, it's a lot of deception, phishing, frauds are happening all over the world. Emerging solution and concern, new biometric method like when pattern recognition are harder to spoof, but AI-driven attacks are still a concern. AI social engineering is one of the big problem also. AI is amplifying, social engineering attacks, making it harder to detect AI-generated content. So these are some of the, important, but I'll go with the focus issues. And then digital arrest is the talk of the town. So scammers utilize advanced deepfake technology to impersonate officers of Indian Central Bureau of Investigation, CBI, and the Chief Justice of India. A person, a businessman who became the victim, he was, of course, educated person, knowing each and everything, but he also knew that who's the Chief Justice, who's the head of CBI. So everyone was, deepfake. So the scheme involved staging a fake trial at the Supreme Court of India using video conferencing tool, making it appear highly convincing. And the SP Oswal, a prominent Indian textile baron, was targeted. The victim was threatened and forced into paying a penalty of $0.833 million as part of the fake trial verdict. So he was arrested and he was convinced that, okay, real CBI personnel, real Chief Justice are, trialing, is giving trial, but if you can pay some money, you will be not arrested. So scammer took the money and disappeared, leaving the victim defrauded. When I was making the presentation, another 3 days before or few days before, another news from India, the lady was, compromised, and 12 lakh Indian currency, 22 lakh Indian currency was also, transferred from this lady. So again, another news was there. Okay, another deception issue, Hong Kong MNC lost around $25.6 million, again in 2024. Multinational firm in Hong Kong lost around 200 million due to scam. Scammer impersonated business partners and deceived employees into transferring large sums. So employee was there, he has access to the system. So all the partners came in the meeting and they say, okay, yeah, this and that. So the fraud was carried out with a high professionalism, including fake identities and convincing documents. So the employee was very much convinced that these are the real, owners, are the, board members, and, the money was transferred. The firm realized the deception only after the fund was transferred. The case highlights the increasing sophistication of the cybercrime and the vulnerability of business to such a scam. So technologies are going very rapidly and very sophisticated. Sophistication is very much there because they knew the owners of the company or the stakeholder of the company, shareholder of the company. They knew the important data, and employee was, convinced that these are the people. They are saying, digital direction. So the employee transferred the money. Okay, again, in last year, 2023, fake Pentagon explosion was viral. So, it affects the stock market. Social media users, including verification experts, pointed out inconsistencies such as the Pentagon's altered appearance and strange effects like a floating lamp post. To stop AI-generated images, experts recommend using tools like reverse image search and analyze details such as landmarks, posture, and environmental factors. So there are certain techniques to make sure that this image is really coming from where, what is the source of the image, and so on. So AI-generated images may also exhibit unnatural features like distorted limbs or unblinking eyes, helping identify fakes. So, I mean, those who are into the cybersecurity, they can really easily, even with a manual without tool, understand the image or the video is not the real, it's a fake. And of course, in the background, you need to verify. Again, another example of last year, Singapore PM promoting crypto video. In December 2023, deepfake video of Singapore Prime Minister Lee Hsien Loong and Deputy Prime Minister Lawrence Wong circulated online. This video became viral, and the video falsely promoted cryptocurrency and investment product. So these AI-generated videos, misrepresented their identities, highlighting the growing misuse of the deepfake technology for scammers. So this is how it is affecting. Three more examples, I'll go with the fake police video call 2022. So a Thai police warned about a scammer using deepfake video call to trick victim into transferring money. Transferring money, how they just appear to be a policeman and having a video call with them. So scammer manipulate public footage, making it appear as though a police officer is calling the victim. Authorities emphasize that the police do not make a video calls or request money in criminal cases. So even those who were victims, they were educated, and interestingly, because of the video call, because they were seeing a deepfake generated police officer, so they become the victim. So victims are urged to report suspicious calls to police hotline for the verification. This is what the authorities want. Pedophiles are using open source AI to create child sexual abuse material. This is again a big problem on the deepfake, because of deepfake, and on the dark web, a lot of CSAM are going on. So they are manipulating images of children, including celebrities or known abuse victims. AI software like Stable Diffusion is being discussed in dark web forum, with users sharing guides and tips for generating realistic CSAM images. Experts warn that AI-generated CSAM may worsen the public health epidemic of online abuse and complicate efforts to identify real victims. So again, this is a very dangerous area where on dark web, CSAM cases are growing, and normally with the majority of cases with the celebrities and their kids. The UK government and safety organizations are concerned about the irreversible proliferation of the open source AI model. So AI models which are open source, they are promoted, and they are generating such type of videos. Some of the software are paid, of course, but there are majority of software are open source, are free, and people are using to get the deepfake or the deception using these tools. Impersonation with the deep video and voice fake. Scammers are using now AI tools, including deepfake technology, to create realistic voice and video. In impersonation of the victim or authority figures to deceive other into transferring the money. So I'm also using with one tool which is free. I'm working on it to create a video and create one social kind of a research paper. So see what is the effect and how people are going to be not understanding the tool-based generated message and the real messages. This AI-driven fraud has led the incidents where victims transferred a large sum, believing they were helping their beloved ones or their friends or the distressed colleagues. Experts warn that the deepfake technology is becoming more accessible, making it easier for scammers to exploit emotions like fear and urgency to manipulate victims. To counter such a scam, individuals should verify suspicious requests through alternative communication channel. While I'm receiving a call from, for example, Dr. Islam, and Dr. Islam is saying, I'm in trouble, just send me $50. So what I can do, I can confirm through another device that, Dr. Islam, are you okay? Are you think fine with you? So if I am going to confirm, and this is happening every time I'm receiving so many social media friends look at, they're already my friends. So what I'm going to do, I'm asking the original, the account and sending them a private message or through mobile, through WhatsApp that, okay, is this your account? They say, no, it's not me. Somebody else created the account. So these are, normal practices. So deceptive AI claims, the Federal Trade Commission has filed complaints against several AI-powered business schemes, accusing them for fraud. So they are working and they are thinking that these companies are, these businesses are doing fraud. Ascend Ecom is alleged fraudulent scheme that promise consumer passive income through AI-driven online stores, defrauding at least $25 million. E-commerce empire building promised to help consumer build an AI-powered e-commerce empire with costly training and online storefront purchases. A writer marketed an AI service for generating fake consumer reviews, leading to deceptive marketing practices. FBA Machine, a rebranded scam from passive scaling that promised AI-powered tool for profitable online. So some of the victims are investing money in these scammed, websites or the applications and losing their money. So these were some of the, examples how deception and what level deceptions are going on. Now, important thing that how to deal with them. What are the countermeasures? What efforts as a scientist, as a researcher, we need to do to overcome these? So I have given some of the aspects, of course, not all, because my expertise on the cybersecurity issues. So I was keeping in view, especially the deepfake, technology. But again, I'm cover some other general, countermeasures also. So coming to the countermeasures. So the first countermeasure is the awareness efforts. So people need to know what is going on, what type of scams are going on. You need to update yourself. So user education, train the public to recognize AI-generated contents and understand its risk. Media literacy program through social media, through electronic media, teach critical thinking skill to evaluate online content for authenticity. Crowdsourcing detection, encourage a collaborative platform where user can report and flag suspicious AI-generated content. So if I'm facing, I can report. Like, some phone calls are coming in Pakistan and they are normally not, masking the phone number. The phone number is not normal, but they are pretending that they are government officials. So very easily we can find out because these numbers are not starting from certain digits. So these are the private numbers. So, but we need to give this awareness to our public. But, normally everyone become the, victim. Ethical use campaigns can promote responsible use of AI in media, advertising, and governance. So these are the awareness efforts. Now coming to the regulatory and policy efforts, AI regulations, for example, support the implementation of AI-specific regulations like the European Union AI Act or similar framework. So we need to work in Pakistan. Also, we do have a PICA rules 2016, and there was amendments, I think, this year. But again, we need to, go through what other countries are doing and how to, handle. So we need a complete framework, a complete SUN team to handle these situations. Standards for AI ethics are important. So we need to adopt international standards. For example, IEEE 7000 series for ethical AI development. So this will help us to understand that what are the AI development tools doing and how can they be misused. So we need to control through these standards. Mandatory disclosures require AI developer to disclose the capabilities, limitation, and risk of their system. So sometimes they are making tools, but these tools are misused. So, there must be some regulations, some policy to restrict those misuse features or restrict through the government agencies or departments. Liability laws define clear accountability for AI-generated harm, including deceptive use. So, for example, who will be responsible if the tool used, now the creator of the tool or the user of the tool who created deep fake movie or video, and so this is very important that we need liability, that who will be responsible of doing so. The companies who are generating these tools should understand that these tools may be misused. So they have to avoid such features in their tools. Audit requirements mandate periodic independent audits of AI system for compliance and security. Disclosure labels require labels on AI generated or AI assisted content, identifying its synthetic nature. So, audit is important. Disclosure is very important, that these tools have these limitations, this scope is this, and so on and so on. And real-time verification system, I'll talk about this, about the tools, how can we control in the real-time verification. So deploy public tools for immediate verification and content authenticity. But this can be from the ISPs, like the internet service provider, or by the the government agencies, telecommunication companies. They can adopt. And currently also in Pakistan, a lot of firewalls are there. They are trying to control these deceptive things. But again, then again, the internet becomes slow. So we need to understand that these policies or these regulatory efforts are positive and helping the community, not disturbing the community. Collaborative efforts, a global framework is very important. So we need to support global agreement to limit the misuse of AI for deceptive purposes. For example, through UNESCO or UNI initiatives, United Nations AI initiatives. So we need to understand that all the countries, especially the third world countries, so we need to understand that United Nations AI initiatives are available. UNESCO is also UNESCO is also working on this. So we need to follow, because this is a global phenomena. It's not the local phenomena. Yes, the cases in other countries are maybe using the very sophisticated tools, but cases in Pakistan or our neighboring countries are not using the sophisticated tools. So we need to learn from others, and then we have to implement so that we can help our community to save from these scammers. Cross-sector collaboration is important, that partners with tech companies, researchers, academicians, policymakers, to share tools and best practices. Then individual organization based, for example, my organization can do what. So organizational efforts are also important, that AI ethics committee is supposed to be there, establish internal oversight bodies to monitor AI development and deployment. Usage restriction, limit AI usage in area prone to deception, like political campaign or sensitive reporting. AI deceptive task force supposed to be there, from dedicated teams to handle cases of AI-related deception or misinformation. Crisis management protocol is important, that we need to prepare a protocol to respond swiftly to widespreading AI-based deception. So as an organization employee, we need to understand that we should have a committee. We restrict the use of the AI technology. We have a task force which is going to monitor the AI deception, and of course the protocol which help us to respond to whatever attack or whatever deception is made. Now, important is the technical efforts. So few of the technical efforts I'm going to talk about today's my talk. Data integrity check is very important. Validate input data to prevent malicious use of AI system. So on the data layer, we need to make the data is correct or not. Sometimes data is partially correct and partially not correct, but that partially correct make the system convince the victim that yes, he is right, because he knew one or two things. Maybe because he forget maybe a few things, but because of his situation or her situation. Bias auditing, perform regular checks for bias and AI training data and model to ensure impartiality. I mean, biasism is not good, but bias auditing, especially for the AI deception tools, is very important. Adversarial testing, regularly test AI system against adversarial attacks to identify vulnerability in the system. So we need to regularly, test these system and see how they are performing, and if they are misused, we can, limit them. Robust algorithms are important. Develop algorithm resistance to tampering and manipulation. So we need algorithm to improve the algorithm so that tampering in the data or tampering in the images or whatever the videos can be identified. Secure API is very important. Application program interface are supposed to be secure. So they limit access to AI model through secure API using and access controls. Digital watermarking is also one of the way we can technically help the community. Embed and check for digital watermarks in AI-generated content to authenticate originality. Blockchain technology is also one of the important way to handle the situation. Use blockchain for content provenance to trace the original of digital media. And then AI detection tools are very important. So I'll not talk about all tools, but some of the important tools. So use AI system designed to detect deepfake, altered images, or sensitive contents. We'll talk about these tools in the next slide. So AI tools, good example is Microsoft Video Authenticator. This tool uses AI to analyze video and detect deepfake or manipulated content. It can identify signs of manipulation like changes in lightning, color, facial inconsistencies, and so on. Deepware Scammer is another tool, a tool designed to detect deepfake videos in real time, developed by the Deepware team. It works by analyzing facial features and comparing them against known characteristics of sensitive media. Another important tool is Sensity AI. Formerly, it was known as Deep Trace. So Sensity provides a platform for detecting deepfake, analyzing videos, and identifying the types of manipulation. The algorithm can flag videos and images that have been digitally altered using AI. So this is a very good tool which help you that, okay, this video is not the real, it is manipulated video or altered videos. Okay, then we have another important tool is the fake catcher, developed by a researcher at the University of California. This deep fake detection tool look at the blood flow in the person's face by analyzing pattern in the pixels, which are hard for AI to mimic, conventionally. This is very, when I was looking at this tool, I mean, if I'm talking to you now and it has the camera and it can, see my facial, and the blood circulation, blood flow. But that when AI generated images of mine will come and say something, it will not showing that blood flow. So this is a very good tool. Then ExceptionNet, a deep learning based tool that can detect deepfake by looking for inconsistency in how faces are rendered in video, such as unnatural blinking or lip movements. So this is again looking at because of course these tools are growing, but again, the natural look is not there in these tools. Then finally, recommendation, experts recommend investing in advanced cybersecurity measures, including multi-factor authentication and encryption, also important to handle such type of, to control and to become the victim. So you need these tools, you need these facts and all the efforts which I talk about from, efforts of giving awareness and training to the normal people, the common people. So these are some of the recommendations. So I'll go with the QA. Over to you, sir.
Thank you, sir, for such a nice and informative talk. From the audience, if you have any question, So I think if there's no question, I thank you, sir, for your time, for your valuable talk. And I handed over the mic to Professor Islam.
Thank you so much, Professor Tariq, for sharing this great presentation. It's always a pleasure to have you with us. Thank you for your support.
Thank you, Dr. Asna. Inshallah, I will see you, inshallah, in the next meeting. Inshallah.
Inshallah, we'll need to make it in person next time. So hopefully we can do it. Thank you.
Thank you. Thank you so much.
Yes,
Thank you.
Thank you, sir. Thank you.
So I think we can have a break until this is the end of Region 10 sessions. So we will move next to Region 8. And it should start maybe just after 1 hour from now. So we can have a break to continue our day. Thank you all and see you soon. Thank you.
Thank you. Thank you, Dr. Islam. Thank you. Thank you.
Thank you. Thank you.